Somewhere in the Milky Way there's a star burning with the power of 10 billion suns, so huge that if you drop it where our sun sits, the planets don't orbit, they vanish. How can anything grow that bright without tearing itself apart? And what does that monster reveal about the limits of physics before the universe says, no further? In deep space, surface is a rumour. Light, gas and dust can impersonate an edge for years, and when a star is extreme enough, that illusion becomes the first danger. Tonight we follow the evidence trail that turns a simple superlative into a scientific dilemma. What does it even mean to measure a star? We will trade awe for instruments, and let units do the arguing. Astronomical units for orbits, solar radii for apparent edges, solar luminosities for power. Because in the realm of hypergiants and newborn titans, size is not a single number. It is a stack of definitions. A photosphere is not a crust. It is the last scattering layer where photons finally stop negotiating with matter. In ordinary stars, that boundary stays tight, but in swollen red giants it frays into a fog bank that breathes. Convection rises in cells large enough to shame continents, then collapses, driving shocks that lift molecules and seed dust. The same star can look larger in one wavelength, smaller in another, and different again a season later. So we will ask a stricter question. Where does the star end when the outside is still flowing outward? To answer, we begin with a thought experiment grounded in scale, placing a real stellar monster at the sun's address, then watching the map of the inner system change. We track what is swallowed first, what is merely scoured by heat, and what dies from drag long before any dense layer arrives. Then we step closer to the boundary itself, where opacity, temperature, and turbulence collaborate to redraw the star from night to night. From there our path moves to Canis Majoris, restless, dusty and asymmetric, a red hypergiant that refuses to hold still for our measurements. We cross to another galaxy to meet WOH G64, a giant behind a veil, where geometry can masquerade as enormity. And we pivot to a different kind of extreme in the Tarantula Nebula, where R136A1 shows how brilliance can be compact, and how radiation pushes back against gravity. Along the way, every claim of largest or brightest will face a checklist of uncertainties: distance, extinction, temperature, crowding, clumping winds, and the models we lean on when we cannot touch. Yet this is not only a problem of bookkeeping. At these limits, the physics begins to strain in observable ways. Winds thicken into pseudo-photospheres, eruptions rewrite envelopes, and light itself becomes a force capable of sculpting a star's destiny. The deeper we go, the more the monsters stop looking like exceptions and start looking like boundary markers, signposts for how stars live fast, shed mass, and leave behind the elements we breathe. By the time we reach their final acts, the question will no longer be merely how big a star can appear. It will be what these brief, violent lives teach us about the architecture of galaxies and about the rules the universe enforces when creation tries to exceed them. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. This journey moves from a solar system scale test to shifting stellar edges, to 3 case studies that challenge every definition we trust. And with each step, the monsters sharpen into measurements, pointing toward the farthest edge of the possible. The sun holds the solar system together, but it also sets our sense of scale, quietly, constantly, and so completely that we forget it is a reference point. In this thought experiment, we remove it and put something else in its place, and the familiar geometry of space becomes suddenly negotiable. Not a fantasy star, not a video game boss, but an observed extreme drawn from real catalogues and real debates. The rules are simple, and they keep us honest. We use measured quantities, we state uncertainties, and we resist the urge to call anything impossible just because it feels too large. Start with the familiar, because familiarity is the only way to feel the shock of replacement. One astronomical unit is the average Earth to Sun distance, defined precisely today through radar ranging and orbital dynamics. It is our yardstick for orbits, heat, and light. And it is the number that turns a diagram into a place. The Sun's radius is 1 solar radius, written R, and it is tied to a photosphere we can actually see. The Sun's luminosity is 1 solar luminosity, written L, and it is the power output that drives climate, photosynthesis, and the slow chemistry of oceans. These are not just units, they are the baseline that makes every claim about a monster star either meaningful or empty. Now replace the sun with a swollen red photosphere, and let the transformation happen in full view. The yellow disk thins, as if its surface were dissolving into smoke, and a deeper red glow billows outward in slow motion. The inner planets do not explode, because space is mostly empty, and gravity does not suddenly vanish. They simply disappear under a surface that is no longer near the centre, swallowed by an object whose surface is a moving target. Mercury is gone first because its orbit is only 0.39 AU, and the new star's outer layers reach past it like a tide. Venus follows at 0.72 AU, and the scene turns from spectacle into geometry. Earth vanishes at 1 AU, and the thought experiment stops feeling like a metaphor. Mars is next at 1.52 AU, and the solar system becomes an interior region of a star. The visuals are clean, but the physics underneath is messy. The red surface is not a polished sphere, and it does not sit still like a solid planet. Convection cells the size of continents, sometimes the size of orbits, churn heat upward and let cooler gas sink back down. Shock waves from pulsations ripple through the atmosphere, and dust can condense where temperatures drop enough for molecules to stick together. Even the colour is a clue, because a cooler photosphere shifts the spectrum toward red and infrared, changing what bright means to a human eye. This is the hook, but it is also a trap. We talk about a star's radius as if it were a hard boundary, like the edge of a billiard ball. For the Sun, that approximation works, because the photosphere is relatively thin compared to the Sun's size. For the largest cool supergiants, it breaks down quickly because their atmospheres are extended, convective, and time variable. Their outer layers can be partly transparent, partly dusty, and partly flowing away in a wind that never really stops. So what is the edge of a star, when the star is more like a gradient than a wall? Is it where the gas becomes optically thick in visible light, meaning photons finally scatter so often that the star looks like a surface? Is it where infrared emission from dust peaks, marking a shell that can sit far above the photosphere? Is it where a model says the photosphere should sit, averaged over pulsations and shocks that push the boundary in and out? When astronomers quote a radius, they are often choosing a definition, then translating light into size, and the translation has a cost. We need scale tools that stay honest, especially when the images start to feel unreal. AU tells us what gets engulfed, because it is tied to orbital distances we can picture. R tells us how many suns fit across a diameter, which is a way of comparing geometry without pretending we understand the atmosphere. L tells us how much energy is coming out per second compared with the sun, which is a statement about power rather than shape. Mass, in solar masses, tells us how much fuel and gravity the star began with, even if it has already lost a great deal. Temperature tells us what colour dominates the spectrum, and it anchors the link between brightness and size through basic radiation laws. Each number answers a different question, and mixing them creates the illusion that one star can be biggest in every way. The title of this film is a provocation, and it is meant to be slightly uncomfortable. 10 billion suns is not a literal pile of 10 billion stars stacked into a single object. It is a luminosity scale idea, a way to ask how bright an object can be in units of L before physics pushes back. Brightness is not size, and size is not mass, even though our instincts try to fuse them. A star can be enormous and relatively dim per square meter, because a cool surface radiates less intensely. A star can be compact and still outshine a galaxy core for a moment, because temperature and opacity can make radiation pour out violently. We will keep separating these concepts until the extremes stop feeling like magic and start feeling like measurable regimes. The first extreme in our cast is Canis Majoris. It is a red hypergiant in the Milky Way, and it is famous because it looks too large to be real when you first see the numbers. It has an irregular envelope, strong mass loss, and a surrounding nebula shaped by eruptions that likely happened within the last few thousand years. That nebula is not just pretty, because it is a record of the star's recent behaviour written in gas and dust. Its distance has been revised, and every revision changes the inferred luminosity and radius, because brightness falls off with distance squared. Its spectrum is crowded with molecular features, including bands from titanium oxide and other compounds that thrive in cool atmospheres. Those features complicate temperature estimates, and temperature feeds directly into radius when you infer size from luminosity. Its outer layers are not a clean sphere, which means the word radius becomes a negotiation between observation and definition. If we put a Vy Canis Majoris-sized photosphere at the Sun's position, the inner solar system is not the only casualty. Depending on which radius definition you adopt, the surface can approach the orbit of Jupiter, and the camera pullback becomes almost absurd. Some estimates place it smaller, some larger, and the uncertainty is part of the story rather than a flaw in it. The point is not to win a record, because records shift as methods improve. The point is to see how close observation can get to a boundary that is physically smeared, and to notice how much of the answer depends on what we mean by surface. The second extreme is WOH G64. It sits in the Large Magellanic Cloud, far outside the Milky Way's disk, and that location matters because the chemical environment is different. It is wrapped in dust, and the dust is not decoration or an afterthought. Dust absorbs visible light and irradiates in infrared, which means the star's apparent brightness depends strongly on wavelength and viewing angle. The dusty torus and outflow geometry matter because they decide what we see and what we miss, like a lampshade that hides the bulb while glowing itself. Its radius estimates have swung as models improved, and the debate reveals how environment and metallicity can change late-stage stellar evolution. In plainer terms, fewer heavy elements can alter how efficiently the atmosphere cools and how winds carry mass away. WOHG64 also forces a practical question that sits at the heart of this chapter. When a star is dust enshrouded, are we measuring the star or its cocoon, and can we tell the difference with confidence? Interferometry can resolve structures, and it can separate a central source from an extended halo when conditions cooperate. Interpretation still depends on assumptions about dust grains, their sizes, their compositions, and how temperature changes with radius. Spectra can diagnose molecules and velocities, and Doppler shifts can reveal outflow speeds in the gas. Yet the line-forming regions can sit far above a photosphere, which means the spectrum may describe the wind more than the star. Even the distance, though better constrained in the Magellanic Clouds than for many isolated Milky Way giants, does not remove all ambiguity. The uncertainty bars are not an embarrassment, they are the boundary between data and story. The third extreme is Rs 136a1. It lives in the Tarantula Nebula in the Large Magellanic Cloud, inside a dense cluster of hot stars where radiation and winds sculpt the surrounding gas into glowing filaments. It is not a red giant at all, and it does not threaten to engulf planets by sheer radius. It is a hydrogen-burning, ultra-massive star with a fierce wind and a surface temperature so high that much of its power emerges in ultraviolet. Its radius is not the headline. Its mass and luminosity are, because they tell us how far nature can push a star while it is still burning hydrogen in its core. It shows that the upper end of stellar power is not only about bloated size, it is about how much mass can assemble, ignite, and avoid tearing itself apart. R136a1 also introduces the idea that luminosity has a ceiling, even if that ceiling is fuzzy. As a star gets brighter, radiation pushes outward on gas and dust, and that push is not philosophical, it is a measurable force. At some point that pressure competes with gravity, shaping winds and limiting growth, especially in layers where opacity is high. The details depend on opacity, composition, rotation, and magnetic fields, and each factor can shift the balance. The result is not a single hard limit, but a set of regimes where stability becomes fragile and mass loss becomes inevitable. When we say 10 billion suns, we're asking how close nature can get to those regimes in the real universe, and how long it can stay there. So the cast spans different kinds of extremity, and that variety is the point. Vi Canis Majoris and WOH G64 challenge the meaning of size in cool, extended atmospheres, where dust and molecules complicate every measurement. R136a1 challenges the meaning of brightness and mass in hot, compact engines, where winds and radiation pressure dominate the outer layers. One threatens to swallow orbits by radius, at least by some definitions of radius. Another threatens to dominate a region by luminosity, flooding nearby space with ionizing photons. The documentary will keep returning to this distinction, because it is where intuition fails first and where language starts to blur. To keep the thought experiment grounded, we will use the same steps each time, like a checklist that prevents us from drifting into myth. We start with distance, because distance sets luminosity once you know how much light reaches us. We use spectra to estimate temperature and composition, because temperature sets the relationship between brightness and radius through well-tested radiation physics. We use interferometry when possible to constrain angular size, then translate that angle into a physical radius using the distance. We use infrared dust emission to account for hidden energy, because absorbed starlight does not vanish. It moves to longer wavelengths. We track how much mass is leaving in winds, because mass loss changes the star's future and can reshape what we think we are measuring. Every method is indirect, and every method carries assumptions that must be stated out loud. This is why the biggest star is always provisional, even when the images look definitive. A radius derived from a cool spectrum can change if the temperature scale shifts by a few hundred Kelvin, because cooler implied temperatures demand larger radii for the same luminosity. A luminosity derived from brightness can change if extinction is underestimated, because dust between us and the star can hide a large fraction of the light. A distance can change with improved parallax or cluster membership, and that change propagates through every inferred property. A star can be asymmetric, and a single radius can mislead by implying a symmetry that does not exist. Even the term hypergiant is partly descriptive, partly historical, and not a strict physical class defined by one equation. The uncertainty is not a footnote, it is the tension that makes the question worth asking, because it tells us where the models are stressed. If these stars sit near the edge of stability, then small measurement changes can flip our interpretation of what is happening. Are we seeing a star in a brief violent phase that will end soon, perhaps on timescales short enough to matter historically? Are we misreading a dusty envelope as a larger photosphere, turning a shell into a surface by mistake? Are we catching a massive star whose wind is already enforcing a luminosity limit, shedding mass as fast as it can burn fuel? Each possibility points to different physics and different limits on what stars can become before they collapse or explode. Return to the swallowed planets, because the image is simple and it deserves to be interrogated. Engulfment depends on radius, but also on how we define the surface and what wavelength we use to locate it. A planet inside a tenuous outer atmosphere is not the same as a planet inside an optically thick photosphere, where photons scatter and the gas becomes truly opaque. Tidal forces, drag, and evaporation depend on density and temperature profiles, not just a line on a diagram. Even the orbit itself would respond, because friction in a dense envelope can steal angular momentum and pull a planet inward. The thought experiment is a doorway, not a conclusion, and it raises a question we can actually test with models. We also need to be careful about time, because the universe does not hold these extremes for long. These phases are short compared with the sun's lifetime, and that contrast is part of the mystery. A red hypergiant can change on human timescales, with pulsations and eruptions that reshape its envelope and brighten or dim it over years. A massive hot star can shed mass rapidly, altering its future in a few 100,000 years, which is brief in stellar terms. The solar system, by contrast, is stable on billion-year scales, and its calmness can trick us into thinking all stars are calm. Putting a monster star at the centre is not a prediction. It is a way to feel the scale of transient extremes and to respect how quickly nature can rearrange a star's outer layers. The deeper mystery is why the universe makes them at all, given how precarious they appear. Stellar evolution models predict paths, but the most luminous and most massive objects test the edges of those models, where approximations start to show. Convection in huge envelopes is hard to simulate because it is turbulent, three-dimensional, and coupled to radiation in complicated ways. Mass loss rates are uncertain, and they control whether a star becomes a red supergiant, a luminous blue variable, or a wolf, rayette star stripped to hotter layers. Binary interactions can mimic single-star extremes, or create them by transferring mass and changing rotation. Cluster environments can build stars that would not form alone, because dense regions encourage mergers and competitive accretion. When we look at an extreme star, we have to ask what history produced it, not just what it is today. So Chapter 1 sets the frame and it sets the discipline. We will not chase records for their own sake, because the record book is always being rewritten. We will treat every quoted radius and luminosity as a measurement with a definition attached, and we will say which definition is being used. We will use AU, R, and L as translation tools, and we will keep mass and temperature in view so the numbers stay connected to physics. We will meet stars that seem large enough to erase the inner solar system, and stars so bright that the phrase 10 billion suns starts to sound plausible. Along the way, we will keep asking what we are really measuring when we point a telescope at a turbulent, dusty, time-variable atmosphere. The thought experiment ends where the science begins, and that boundary is the true subject of this chapter. If the sun can be replaced on paper, then the next question is what we are really replacing. Are we swapping a clean photosphere for a layered atmosphere, where light escapes from different depths at different wavelengths? Are we swapping a stable boundary for a wind-driven gradient, where the surface is an average over motion? Are we swapping a simple star for a system shaped by dust, rotation, and companions, where geometry matters as much as temperature? The edge of a star is not a line. It is a problem we have to define before we can measure. Transition. We pull back from the vanished planets and focus on the boundary itself, because the boundary is where the arguments live. In the next chapter, we ask what astronomers mean when they say a star has a radius. Chapter 1 replaced the Sun and erased familiar orbits with a single swollen glow, a red-orange presence that felt more like a horizon than an object. Now we face the harder question behind that image. Where does a star end when its outer layers behave like weather? For planets, edges are surfaces you can touch, or at least map with radar and gravity fields, until the numbers close into a clean outline. For stars, the edge is a definition that depends on light, because what we see is not rock but radiating gas. The boundary we draw is often the place photons finally escape, and that escape is a process rather than a moment. Astronomers call that apparent surface the photosphere, a word that sounds solid even when it is not. It is not a crust or a skin, and it is not a sharp discontinuity in density. It is the layer where photons last scatter often enough to lose memory of deeper regions, so the light begins to carry information about the outer atmosphere instead. A photon born deep inside a star does not fly straight outward like a bullet. It ricochets through plasma, absorbed and re-emitted or scattered again and again, taking a random walk that can last thousands to millions of years in some stars. Only near the outside is the gas thin enough that the photon's final interactions become rare, and then the light finally streams freely. In the Sun, the photosphere is thin compared to the Sun's radius, so our diagrams look honest. It is only a few hundred kilometers thick against a radius of nearly 700,000 kilometers, a razor-thin shell by stellar standards. That thinness makes the Sun feel like a clean sphere in textbooks, and the approximation works because the optical depth changes rapidly with height. Optical depth is the quiet quantity behind that neatness. It is a measure of how many chances a photon has to be stopped or redirected as it tries to leave, and it falls steeply in the Sun's outer layers. When optical depth drops below about 1, the gas becomes transparent enough that the star's surface appears to snap into place. Cool supergiants break that comfort, and they do it in a way that is visually unsettling. Their atmospheres are extended and dilute, and the transition from opaque to transparent can stretch across a large fraction of the star. The photosphere becomes a zone, not a line, and the star's edge starts to look like fog. Imagine a giant ember wrapped in layers of drifting smoke, where the brightness fades gradually rather than stopping. In a red supergiant, the gas is so puffed up that a small change in density can shift the last scattering height by enormous distances. When we ask for the radius, we're really asking which layer we mean, and why that layer deserves the name. Convection is part of the reason, and it is not the gentle convection of a pot of water. In a red supergiant, energy rises through enormous convective cells that churn the outer envelope, each cell spanning a significant fraction of the star's radius. Hot material rises, cool material sinks, and the surface brightness pattern shifts with time, so the star's face can look mottled and alive. Those convective cells are not just pretty texture in an artist rendering, they change the local temperature and density, which changes the local opacity, which changes where photons escape. A bright patch can be a window into deeper layers, while a darker patch can be a thicker veil, and the apparent limb can ripple as those patches evolve. Pulsations add another layer of motion, and they turn the atmosphere into a breathing instrument. The star can expand and contract on timescales of months to years, driven by instabilities in how radiation and gas pressure share the work of support. Those pulsations drive shocks that travel outward through the atmosphere, compressing and heating gas as they go. When a shock passes, it changes density and temperature in a moving front, and that changes where light can escape. A layer that was transparent can become opaque for a time, and an opaque layer can thin and open. The photosphere is dynamic, and it is wavelength dependent, so the star's apparent size can shift with both time and colour. Visible photons may last scatter at one height, while infrared photons can emerge from deeper or higher layers, depending on which molecules and dust grains dominate absorption. Radiophotons can trace still larger structures, where the gas is so thin that only certain transitions glow. A single radius can hide that complexity, yet our language keeps trying to compress it into one number. Opacity is the key word underneath every radius claim, and it is more subtle than how much stuff is in the way. Opacity measures how strongly matter blocks radiation through absorption and scattering, and it depends on the microscopic physics of atoms, ions, molecules, and grains. When opacity is high, photons random walk and the star looks like a surface, because the light cannot reveal what lies beneath. Opacity is not constant, and it does not even vary smoothly. It depends on temperature, density, and composition, and in cool stars it is shaped by molecules that do not survive in hotter photospheres. Titanium oxide bands, water vapour, carbon monoxide, and other species can dominate certain wavelengths, carving deep troughs into the spectrum and reshaping the apparent continuum. That molecular opacity can make the atmosphere appear larger in some bands, because the last scattering surface moves outward where absorption is strong. It can also make temperature estimates harder, because the spectrum is crowded and line-blanketed, leaving fewer clean windows for a reliable continuum fit. The same star can look different depending on the filter, and the difference is not an instrumental flaw. This is where intuition about brightness fails, because our eyes are trained on everyday surfaces. A star can be enormous and still not look blinding per square metre, even when its total power output is staggering. The reason is basic radiation physics, and it has a simple scaling that hides a dramatic consequence. The Stefan-Boltzmann law links luminosity, radius, and temperature, and it is one of the few equations that can be spoken aloud without losing meaning. Luminosity scales with surface area times temperature to the fourth power, which means small temperature changes matter enormously. In symbols, L goes like R squared times T to the fourth, and the fourth power is the lever. Lower temperature is a powerful dimmer, and the numbers are unforgiving. If a photosphere is cooler by a factor of 2, the emitted power per unit area drops by 16, even before we think about dust or distance. A star can compensate by inflating its radius dramatically, turning low surface brightness into high total luminosity through sheer area. That is why red supergiants can be huge without matching the surface intensity of hot stars, and why largest does not automatically mean most energetic per square metre. Their light shifts toward red and infrared as the peak of the blackbody curve slides to longer wavelengths. Brightness becomes a question of wavelength and distance, and human vision is a biased detector. In visible light, a cool supergiant can look strangely subdued, like a lantern behind tinted glass. In infrared, the same object can blaze, because that is where its thermal emission naturally concentrates. When we compare stars by eye, we're comparing them through a narrow biological filter, not through the full energy budget. But even that clean law assumes a clean surface, and the larger stars are often not just stars. They are stars plus outflows, where the environment contributes light and hides light at the same time. The atmosphere becomes an interface between the star's interior and the surrounding space, and that interface can be thick enough to matter. Mass loss is the defining feature of the late supergiant extremes, and it is not a gentle leak. Dense winds carry gas away continuously, and episodic eruptions can throw off shells, arcs, and knots that drift outward like slow fireworks. The star becomes surrounded by its own history, and the history is written in dust and molecular gas. Winds in cool hypergiants can be slow but thick, moving tens of kilometers per second rather than thousands. Pulsations and shocks can lift material to heights where gravity is weaker and cooling is easier, and where radiation can push more effectively. Once gas reaches those regions, it can drift outward and never return, turning the outer atmosphere into a one-way flow. Dust can form in that escaping material, but only when conditions are just right. When temperatures fall enough, atoms and molecules stick into grains, and those grains change the radiative balance because they interact strongly with starlight. Dust absorbs visible light and re-emits in infrared, converting a star's glare into a warm glow that can extend far beyond the gas photosphere. That dust emission can mimic a larger star, especially when our instruments cannot cleanly separate the central source from its envelope. If you measure a bright infrared halo and treat it as photospheric light, you inflate the radius without noticing the substitution. If you ignore dust extinction, you underestimate luminosity and misjudge size, because the star's power has been rerouted into wavelengths you did not count. So the measurement problem is not a technical footnote, and it is not merely about better telescopes. It is the core mystery behind record-setting radii, because the biggest stars are wrapped in winds, molecules and dust that blur the line between star and nebula. When the boundary is smeared, the record book becomes a debate about definitions. We pull back from the vanished planets and focus on the boundary itself, because the boundary is where the arguments live. In a sense, the edge of a supergiant is a laboratory for radiative transfer, fluid dynamics, and chemistry, all operating at once. The question is not only how big, but which layer is doing the shining. To measure a radius, astronomers combine several indirect tools, because no single observation answers the full question. Each tool answers a different part of the puzzle, and each comes with assumptions that can quietly dominate the final result. The final number is a synthesis, and the synthesis can be fragile when the object is complex. Spectroscopy is the first pillar, and it is often the most information-rich. A spectrum reveals temperature indicators, chemical composition, and the presence of molecules, because each species leaves a distinctive pattern of absorption or emission. It also reveals motion through Doppler shifts, which can diagnose winds and shocks, and it can hint at turbulence through line broadening. In hot stars, spectral lines can show broadening and blue-shifted absorption from fast outflows, a signature of gas accelerating toward us along the line of sight. In cool supergiants, molecular bands dominate and complicate the continuum, and the spectrum can describe the wind as much as the photosphere. Even the act of defining a continuum becomes a modelling choice when line blanketing is heavy. Spectra also carry clues about where the light formed, because different lines form at different depths and temperatures. Some features arise near the photosphere, while others arise in the extended atmosphere or the wind, where densities are lower and velocities can be higher. When those layers overlap in the beam, the spectrum becomes a layered conversation, and we have to decide which voice we trust. Interferometry is the second pillar, and it is the technique that tries to turn stars from points into disks. By combining light from separated telescopes, astronomers can resolve tiny angular diameters, sometimes only a few milliseconds across. That angular size can be translated into a physical radius if the distance is known, which is a powerful if. Interferometry also exposes asymmetry, and that exposure can be uncomfortable. A star can appear elongated, mottled, or surrounded by a halo, and the halo can be bright enough to bias a simple diameter fit. If the brightness distribution is not a simple disk, the concept of one diameter becomes a modelling choice, and different models can yield different radii. Even the limb of a star is not guaranteed to be a clean curve in interferometric data. Limb darkening, molecular layers, and scattered light can soften the edge, and the visibility curve can reflect that softness. The star's size becomes the best-fitting parameter in an equation that assumes something about the atmosphere, and assumptions are where disagreements begin. Distance is the third pillar, and it is often the weakest link in the chain. Parallax can measure distance directly for nearby stars, but giant stars are often far and embedded in dusty regions, where optical measurements struggle. Small parallax errors become large distance uncertainties, and those uncertainties propagate into every derived property. Radius depends on distance linearly when you convert an angular diameter into kilometers, so a 10% distance change means a 10% radius change. Luminosity depends on distance squared when you convert observed flux into power, so the same distance revision can shift luminosity by 20%. Then the inferred radius can shift again through the Stephan-Boltzmann relation, because temperature estimates are not perfectly fixed. For many extreme stars, distance has been debated through multiple methods, and the history of those debates is part of the story. Cluster membership can suggest one distance if the star seems to belong to a known group, while master motions can suggest another by tracing geometric expansion in the circumstellar gas. Gaia parallaxes can disagree or evolve with new calibrations, and each update can move a star up or down the size rankings. Infrared observations form the fourth pillar, and they are essential because dust is a selective thief. Infrared light penetrates dust better than visible light, and it directly traces warm dust emission from the circumstellar envelope. It helps recover energy that has been absorbed and re-radiated, allowing a more complete accounting of the star's output. But infrared adds its own ambiguity because dust shells are not simple spheres. They can be extended, clumpy, and asymmetric, and their temperatures vary with radius, composition, and illumination. A bright infrared source might be a compact photosphere or a larger dusty structure, or both, and separating those components is an interpretive act. So the observational story becomes a negotiation, and the negotiation is not a weakness of astronomy. We infer temperature from spectra that may be wind-contaminated, and we infer size from angular diameters that may include halos. We infer luminosity from flux that may be extinguished or reprocessed, and then we try to make the pieces agree without forcing them. This is why defining a stellar surface is not pedantry, even if it sounds like a debate about words. It is the difference between a star that swallows Jupiter and a star that only swallows Mars, and that difference changes how we imagine its place in a planetary system. It is also the difference between stable evolution and imminent disruption, because inflated atmospheres often signal stress. Astronomers use several working definitions of radius, and each definition is a compromise with physics. One is the Rosland radius, tied to an average opacity and an optical depth near 2/3, which is a practical proxy for where the star becomes transparent. Another is a continuum radius at a chosen wavelength, where the atmosphere becomes opaque in that specific band. These definitions can disagree in extended atmospheres, and the disagreement is not a rounding error. Molecular layers can push the apparent radius outward in specific bands, making the star look larger in the optical than in the near-infrared, or vice versa. Dust can add a pseudo-photosphere that is not the star's gas surface at all, but an optically thick layer in the outflow. The phrase pseudo-photosphere matters in the most extreme cases, because it changes what we mean by the star. If mass loss is high, the wind itself can become optically thick, and then the last scattering surface sits in the outflow. The apparent surface is no longer a layer in hydrostatic balance, but a moving boundary in a flowing atmosphere. At that point, size becomes a property of the wind density profile, not just the underlying stellar structure. A stronger wind moves the apparent surface outward by increasing optical depth, while a weaker wind pulls it inward, even if the core luminosity hardly changes. The star can seem to swell or shrink as the wind thickens or thins, a visual effect driven by radiative transfer. This turns radius into a time variable, and time variability is a clue rather than a nuisance. If the mass loss rate changes, the optical depth structure changes, and the apparent photosphere can move. In some cases, an observer could watch the star's edge drift outward over years, then recede as if the star were breathing through its own wind. The environment can also be shaped by direction, because mass loss is not always symmetrical. Outflows can be bipolar, clumpy, or concentrated in arcs, and the dust can form in patches where conditions favour condensation. If we view the system through a denser region, extinction rises, and the star appears cooler and larger, because the light is reddened and the effective photosphere shifts. This is the illusion of size, and it is not a trick or a mistake. It is physics acting through radiative transfer, where photons interact with moving material that can absorb, scatter, and re-emit them. Light does not simply leave a star. It fights its way out through material that may be flowing, cooling, and changing its chemistry as it goes. The biggest cool stars therefore become star plus outflow systems, and the phrase is meant literally. The central object, the extended atmosphere, the wind, and the dust shell all contribute to what we detect, and they can contribute in different proportions at different wavelengths. The boundary is a gradient, and the gradient is evolving, so a single radius is always a snapshot of a particular definition. This is the hook, but it is also a trap, because our language wants clean edges. When we say a star has a radius, we smuggle in the idea of a crisp limb like a planet's horizon. In the most extreme supergiants, that limb can be a statistical surface, defined by where photons have a certain probability of escaping. To keep the story honest, we need one more concept that limits extremes from the inside out. That concept is the Eddington limit, and it is about a balance of forces that can be explained without losing its power. It is also a reminder that a star's brightness is not just an output, but an active participant in the star's structure. Gravity pulls gas inward and holds a star together, and in a massive star, gravity is doing heroic work. Light pushes outward, because photons carry momentum and can transfer it to matter when they scatter or are absorbed. The brighter the star, the stronger that outward push becomes, and at high luminosity the push is not negligible. In many layers, photons push mainly by scattering off electrons, because free electrons are abundant in ionized gas. That electron scattering opacity is relatively simple, and it provides a baseline for discussing stability. If the luminosity is high enough, radiation pressure can nearly cancel gravity, and when that happens, the outer layers become unstable and prone to strong winds. The Eddington limit is the luminosity where radiation pressure matches gravity for a given opacity, and it is a threshold in behavior rather than a rigid wall. It is not a universal number, because opacity depends on composition and ionization, and those change with temperature and depth, but it sets a regime where stability becomes precarious, and where small changes can have large consequences. For the brightest stars, living near that regime changes everything, because mass loss becomes a strategy for survival. Mass loss can become self-reinforcing, because shedding mass lowers gravity while luminosity stays high, pushing the star closer to instability. The star can hover near the limit by blowing off its own envelope, trading mass for stability. In cool hypergiants, opacity sources can spike in certain temperature ranges, and those spikes matter. Molecules, partial ionization zones, and dust formation can increase opacity locally, making radiation pressure unusually effective in specific layers. Even if the global luminosity is below the classical limit, parts of the atmosphere can behave as if they are near it, and those layers can inflate or launch material outward. So the Eddington idea connects directly to the boundary problem, because a star near the limit is more likely to have a dense wind and an inflated atmosphere. The edge becomes less like a surface, and more like a moving photospheric radius in the outflow, shaped by how matter and radiation negotiate passage. The largest stars may be those whose winds are most effective at building a luminous extended veil. Now we can set up the controversy that will carry us forward, and it is a controversy built from real complexity rather than sensationalism. VY Canis Majoris became famous as a candidate for the largest known star, a name that invites a simple ranking. It also became a case study in how measurement choices create apparent monsters and how definitions can inflate a legend. The first issue was distance, and the history of that distance is a reminder of how astronomy improves in steps. Early estimates placed VY Canis Majoris at a distance that implied extreme luminosity, and extreme luminosity invites extreme radius when temperature is low. Later revisions, including measurements tied to masers and improved astrometry, shifted that distance and reshaped the inferred radius. Because luminosity scales with distance squared, a distance change is not a small correction that stays politely in the margins. It can cut luminosity dramatically or raise it dramatically, and then it changes the inferred radius through the same scaling laws we rely on for every star. When the distance moves, the star's position on the Hertzsprung Russell diagram moves with it, and that changes the story we tell about its evolution. The second issue was geometry, and it is visible even in images that are not meant to be technical. VY Canis Majoris is not surrounded by a smooth spherical shell that would make modelling easy. It has asymmetrical ejecta, arcs, knots, and dusty clumps that scatter and emit light, creating a complex scene around the star like debris caught in a slow storm. Those structures contaminate simple measurements, because a telescope may collect light from the star and from nearby dusty emission in the same beam. Interferometry may resolve a bright core plus an extended halo, and the interpretation depends on what you call the star and what you call the environment. If the halo is bright in the band you observe, then the diameter you fit can quietly become the diameter of star plus dust. The third issue was temperature, and temperature is the hinge in the Stefan-Boltzmann law. Cool supergiant temperature scales are uncertain, and molecular bands complicate the continuum, so different analyses can yield different effective temperatures. A few hundred Kelvin difference changes the inferred radius for the same luminosity, and the star can swing from enormous to merely huge without changing its true physical state. The result was debate, not because astronomers were careless, but because the object is physically complex and our tools are indirect. VY Canis Majoris is a system in motion, and our definitions were built for cleaner stars with thinner atmospheres. The controversy is a lesson in how boundaries fail, and how science progresses by tightening definitions when nature refuses simplicity. This chapter is not trying to crown a champion, because the crown itself can be made of fog. It is trying to show why the record book keeps changing, and why the changes are meaningful rather than embarrassing. When the edge is a gradient, the biggest star is partly a question of what you count, and partly a question of what your wavelength reveals. So we return to the central question with sharper tools, and with more humility about what surface means. How can stars become so enormous and bright that they seem capable of swallowing a planetary system, at least in our imagination? What do these extremes reveal about physics, evolution, and limits, and what do they reveal about the way we measure? The answer begins with definitions, because definitions are the handles we use to lift reality into language. A photosphere is a last scattering surface, not a wall, and it is defined by probability rather than by solidity. Opacity makes that surface wavelength dependent, and cool atmospheres make it extended and time variable. So the edge is a moving target. The answer continues with scaling laws, which are simple enough to memorize and deep enough to reshape intuition. Luminosity depends on radius and temperature matters to the fourth power, so cool stars must be large to be bright. A cool star can grow huge without matching the surface intensity of a hot star, because it trades temperature for area. The answer deepens with mass loss, because mass loss changes what we see and what the star becomes. Winds, pulsations, and shocks loft material outward, and dust forms in the outflow when the gas cools and condenses. The star becomes a star plus outflow system, whose apparent size can be set by the wind, and whose light can be filtered and re-emitted by its own debris. The answer is measured through imperfect instruments and careful inference, and the care is part of the drama. Spectroscopy diagnoses temperature, composition, and wind speeds, but it can mix signals from multiple layers. Interferometry constrains angular size and asymmetry, but it must model halos and limb darkening. Parallax and distance ladders set the scale, and errors propagate into radius and luminosity in predictable, unforgiving ways. Infrared data recovers hidden energy and maps dusty shells, which is essential when dust is thick and the optical view is misleading. It also tempts us to confuse dust glow with photospheric light, especially when the envelope is bright and structured. Every method must state what layer it is actually probing, or the final radius becomes a number without a physical home, and above it all sits a stability idea, quietly shaping the most extreme cases from within. As luminosity rises, radiation pressure pushes outward harder, and near the Eddington regime the outer layers can become fragile. Mass loss becomes a way to survive, but it also becomes a way to blur the boundary, turning the star's edge into an evolving surface in a flowing wind. Now that size is complicated, we move to a star that looks like a living storm. We move to VY Canis Majoris and ask what we truly know, and what we only think we know because our definitions are comfortable. The next step is not to pick a single radius, but to map the layers that compete to be called the surface. We do not begin with a number, because numbers can hide assumptions in their neatness. We begin with a boundary, because the boundary is the mystery we can test, and because in stars like these the boundary is where the physics is loudest. We pull back from the vanished planets and focus on one real address. VY Canis Majoris sits in the Milky Way's disk, in the direction of Canis Major, where the winter sky looks deceptively calm. To the naked eye, that patch of sky feels empty, yet telescopes reveal a layered corridor of stars and dust. On a star map it is only a point, but the line of sight cuts through crowded spiral arm structure and stacked drifting clouds. That dust is not a cosmetic haze, it is the raw material of star formation and the ash of earlier stellar deaths. Grains of carbon and silicates, forged in older outflows, float like soot and scatter blue light more efficiently than red. In wide-field imagery, the region looks mottled and bruised, with dark lanes that swallow starlight and bright patches where gas fluoresces. Hydrogen glows in deep reds, oxygen can tint the scene teal, and the whole field hints at ongoing recycling. VCMA lives in that kind of neighbourhood, where massive stars are born fast, burn hard, and leave quickly. Even the calmest-looking constellation can hide a violent ecology, and this one does. Distance matters first, because every extreme claim scales with that single number, and the scaling is unforgiving. When astronomers revise the distance, they are not merely moving a dot on a map. They are changing the star's inferred power output. Modern estimates place it roughly around a kiloparsec plus or minus, and that plus or minus is not a footnote. A kiloparsec is about 3,260 light years, so even small percentage shifts translate into enormous physical changes. Parallax, the tiny annual wobble against background stars, is the cleanest geometric yardstick, but it is hard at this range. Crowded fields, dust extinction, and a bright surrounding nebula can all complicate how that wobble is extracted from data. Flux falls off with the square of distance, which means luminosity rises with the square of distance as well. If the distance is larger than assumed, the star must be intrinsically brighter to look as bright as it does. And if luminosity changes, the radius we infer from temperature changes too, because those quantities are chained together. So one revision can ripple through every headline number, quietly rewriting the story without changing the star itself. That chain is simple in principle and treacherous in practice. The Stefan-Boltzmann relation links luminosity to surface area and effective temperature, but it assumes a definable surface. For VCMA, the very idea of a single surface is part of the mystery, because the star is not isolated. It is embedded in its own debris, and that debris both blocks light and manufactures new light in the infrared. Some photons escape directly, some are scattered into our line of sight, and some are absorbed and re-emitted at longer wavelengths. So before we talk about size, we have to talk about what we are actually seeing. VCMA is not a clean sphere with a tidy limb, like a textbook diagram with a crisp edge. It is a star plus an environment, stitched together by outflow, scattered light, and dust that acts like a shifting veil. Around it sits a complex nebula of arcs, knots, and asymmetric ejecta, lit from within like smoke caught in headlights. In optical images, the structures look like torn ribbons and curved splinters, each one angled as if thrown by a different hand. Some arcs appear brighter on one side, as though the illumination is uneven, or the dust is thicker in certain directions. In infrared views, the scene changes again, and the same region becomes a glowing map of warm dust grains. The glow is thermal, not magical. Grains warmed by starlight re-radiate like tiny furnaces, each with a temperature signature. Those structures are not background decoration, because they are the star's recent history written in matter. If you could watch for centuries, you would see the pattern slowly unfold like a slow-motion explosion. Some features trace discrete episodes, not a smooth wind that never changes, and that difference is crucial. A steady wind would paint a more uniform shell, but VCMA's nebula is lopsided and clumpy. Clumps imply density contrasts, and density contrasts imply that the launching mechanism varies across the surface and over time. The nebula acts like a time capsule, with material launched decades to centuries ago still expanding into space. When we measure the proper motion of a knot, we're watching a past event continue to unfold in the present. Spectra add another dimension, because Doppler shifts reveal which clumps are moving toward us and which are sliding away. That is part of the unsettling beauty here. This star's archaeology is young enough to be timed with human calendars. It invites a strange thought. Some of the ejections began when telescopes were still crude and the physics was unknown. Now that size is complicated, we move to a star that looks like a living storm when you translate its physics into imagery. VCMA is classed as a red hypergiant, a late stage for very massive stars that have already left the main sequence behind. The term hypergiant is not just a boastful label, because it signals instability and extreme mass loss as defining traits. These stars have swollen envelopes, low surface gravity, and atmospheres that are easy to disturb, like loosely packed ash. The outer layers are only weakly bound, so modest pushes can loft gas outward and keep it from falling back. In a sense, the star is balanced between being a star and being a wind, and it cannot fully choose. Convection dominates the envelope, and the convective cells can span a large fraction of the radius, not just a small surface granulation. On the Sun, convection makes a fine, boiling texture, but on a hypergiant the boil becomes continental in scale. A single cell can be so large that it changes the star's brightness pattern from one hemisphere to another. Hotter, upwelling regions shine more strongly, cooler sinking regions dim, and the pattern can evolve over months or years. That convection makes the surface patchy in temperature, and patchiness changes opacity in ways that are hard to average away. Opacity determines how far photons can travel before they scatter or get absorbed, which sets the depth we effectively see. So the apparent edge shifts with wavelength, because different wavelengths probe different depth through the same turbulent atmosphere. What looks like a boundary is often just the place where the fog becomes too thick for light to cross. A red hypergiant is not simply a bigger red supergiant, because the regime itself changes the rules of stability. It is a domain where mass loss and atmospheric inflation becomes central to the star's identity, not incidental side effects. The star hovers near limits set by radiation pressure, opacity peaks, and weak gravity, and those limits are not abstract. Radiation pressure is the momentum carried by light, and in luminous stars it can push outward almost as effectively as gas pressure. In certain temperature ranges, opacity rises sharply because of ionization states and molecular contributions, which makes radiation pressure more potent. Ion group opacity bumps and molecule-rich layers can act like traps for photons, letting pressure build where the gas is already fragile. Local layers can behave as if they are near the Eddington balance, even if the whole star is not. That means the star can be stable in one layer and unstable a little higher up, like weather stacked in vertical sheets. The Eddington idea is simple to say and difficult to live with. If outward radiation force matches inward gravity, the layer is neutrally supported and any extra push can unbind material. When that balance tips, the atmosphere inflates, shocks form, and outflow becomes easier, sometimes catastrophically easier. Pulsations can amplify this, because a swelling envelope changes density and temperature, and those changes feed back into opacity. The result is a boundary that moves, and a system that records its own disruptions in dust and gas. VCMA is compelling because it sits near that knife edge where the star's own light can help dismantle it. It is stellar self-erosion, driven not by impact, but by the relentless pressure of photons. Numbers anchor the intuition, but they must carry their uncertainty openly, because the uncertainty is part of the physical story. Radius estimates for VYCMA are often quoted in the rough range of 1,000 to 2,000 solar radii, and that spread is not trivial. Different methods and definitions push that range, and the spread is part of the lesson about measurement in messy systems. A radius can mean the continuum photosphere, a molecular layer where opacity spikes, or a pseudo-photosphere in a thick wind. Each one is real in its own way, but each one answers a different question about what we mean by the star. Even the word photosphere is a convenience here, an optical depth threshold, not a hard surface you could land on. At the low end, the photosphere could engulf Mars if placed where the Sun is, swallowing the orbit that feels safely distant in our minds. At the high end, the implied surface can reach toward Jupiter's orbit in the thought experiment, crossing a scale we usually reserve for planets. That does not mean Jupiter would sit inside a solid wall, because the outer layers are dilute and more like fog than rock. It means the last scattering surface in a chosen band could lie at that scale, where photons finally escape freely. If you could fly through the outer envelope, the density would rise gradually, and inside would be a slow transition, not a door. Gravity would feel surprisingly gentle near the edge, because the mass is spread over such an enormous volume. And yet the radiation field would be intense, light pushing outward, heat soaking everything, and dust grains struggling to survive. Luminosity is also extreme, commonly in the hundreds of thousands of solar luminosities, and that power output reshapes everything around it. That power is not a record by itself, because hotter stars can be even more luminous, but it is enormous for a cool star. Cooler surfaces radiate less per square meter, so the star must be huge to shine that much, like a dimmer bulb made vast. This is the Stefan-Boltzmann trade, and it is why temperature debates matter so much for this object. Shift the effective temperature by a few hundred Kelvin, and the inferred radius swings hard because area must compensate. A small change in temperature can mean a very large change in surface area, and that is where the drama hides. The same observed flux can imply a smaller, hotter star, or a larger, cooler one, and both can fit parts of the data. That ambiguity is not just a mathematical curiosity, because it changes how we place the star on evolutionary tracks. Evolutionary tracks are theoretical paths across the Hertzsprung, Russell diagram, and they encode assumptions about mass loss and mixing. Mixing matters because it controls which elements reach the surface, and those elements influence opacity, cooling, and dust chemistry. If we misplace VYCMA, we misread its past and we mispredict its future, including the kind of supernova it might produce. So the argument about temperature is also an argument about fate. So how do we infer what VYCMA actually is, when its own environment keeps editing the light we receive? We start with the spectral energy distribution, because the energy budget spans many wavelengths and each band tells a different truth. In visible light, dust and molecular bands can suppress the flux and distort the continuum, making the star seem dimmer and redder. The spectrum is crowded with molecular absorption features, especially from titanium oxide in cool atmospheres, which complicates temperature fits. Those bands are not just labels in a plot. They are fingerprints of temperature, pressure, and chemistry in the outer layers. In infrared, the system brightens because dust absorbs starlight and re-radiates it thermally, shifting energy into longer wavelengths. So the star can appear to move across the spectrum, not because it travels, but because energy is being redistributed. That re-radiation does not create extra energy, but it moves energy into bands we must count if we want the true luminosity. Dust grains heat up until they reach a temperature set by the balance of absorption and emission, then glow like embers. Some dust is close and warm, radiating in the near-infrared, while cooler dust farther out glows at longer wavelengths. The infrared peak can even act like a calorimeter, hinting at how much starlight is being intercepted and processed by the envelope. If we ignore infrared, we underestimate luminosity and misplace the star on evolution tracks, making it look less extreme than it is. If we treat dust emission as photospheric light, we overestimate radius and invent a larger surface that is not physically there. So the same dust that helps us close the energy budget can also mislead us about geometry, unless we model it carefully. Effective temperature is debated because the spectrum is crowded and the geometry is messy, and both problems feed into each other. Molecular absorption, especially in cool atmospheres, makes continuum placement model dependent, because there may be no clean continuum at all. Scattered light from the nebula can contaminate what looks like direct starlight, adding a faint redistributed component. A dusty line of sight can redden the star, making it appear cooler than it is, unless the extinction is modelled carefully. That extinction is wavelength dependent, and grain size matters. Small grains redden strongly, larger grains flatten the curve. Different teams choose different atmospheric models, and the results do not always converge, even with excellent data. The disagreement is a clue that the star's outer layers are not behaving like the simplified atmospheres we learned first. This is not failure, because the star is not a textbook object with a simple atmosphere and a single temperature layer. It is a stress test for radiative transfer, convection, and dust physics at once, all operating in a regime near instability. The models must account for non-uniform surfaces, extended molecular layers, and outflows that can be optically thick. Even the phrase effective temperature becomes slippery, because it is an average that may not correspond to any single physical layer. In plain terms, the star has many skins, and each wavelength tells us about a different one. So the debate is also a reminder of what astronomy often is: inference under imperfect, evolving assumptions. Interferometry and high-resolution imaging add structure to the argument, because they can resolve what a single telescope blurs together. By combining light from separated telescopes, interferometers achieve the resolving power of a much larger instrument. They can separate a bright core from an extended halo, but interpretation still depends on wavelength and on how the brightness is distributed. A diameter measured in one band can trace molecular layers, not the deeper continuum photosphere that we might want for a radius. A diameter measured in another band can be smaller because opacity is lower there and we see deeper into the atmosphere. Even calibration becomes delicate because the surrounding nebula can leak into the measurement and inflate the apparent halo. The star's apparent size becomes a function of what the instrument is actually sensitive to, which means radius can be an observational artifact. So one number called radius can hide multiple physical layers with different meanings, each one real within its own definition. This is why headlines about a single, definitive size are so fragile, because they compress a multi-layer system into one digit. If you change the wavelength, you change the depth, and if you change the depth, you change the radius you report. VOSI CMA forces that lesson into the open, because its atmosphere is so extended that the differences become dramatic. It is not that the star is inconsistent, it is that our questions are unless we specify what surface we mean. The nebula raises the stakes because it implies recent violence, not just gentle breathing. Arcs and clumps suggest episodic ejections, not only a steady outflow, and episodic ejections demand a trigger. Proper motions and expansion speeds can date features. turning geometry into a timeline that stretches back centuries. That timeline points to instability on humanly imaginable timescales, not only geological ones, which makes the star feel uncomfortably alive. When you watch a knot drift outward, you're watching the aftermath of an outburst that may have occurred before modern science existed. The nebula becomes a slow-motion record of a star that cannot keep its outer layers quiet. Mass loss rates inferred from dust and gas can be high enough to reshape the star's future, because the envelope is the star's vulnerable skin. Losing the envelope changes the path towards supernova, and it changes what kind of supernova occurs, because the explosion interacts with what remains. If the envelope thins, the star may evolve blueward, becoming hotter at the surface even as it approaches core collapse. If dense circumstellar material surrounds it, the eventual shock can light up that material and create unusually bright emission signatures. The brightness would not be only from the explosion itself, but from the collision between ejecta and the material already shed. VUE-Simmer becomes a lesson in how massive stars approach the end while shedding their outer layers, piece by piece. There is also a deeper implication hiding in the dust. Dust formation requires certain temperatures, densities, and chemical ingredients, and those conditions are met in the cooling outflow. As gas expands, it cools, molecules assemble, and then solids condense, an astrophysical version of smoke forming from hot breath. So every infrared bright arc is not only a record of mass loss, but a record of chemistry in motion, turning gas into solid grains. Those grains can later seed future star-forming clouds, meaning the star is already contributing to the next generation of objects. Even in its instability, VY-CMA is part of the galaxy's recycling system, converting nuclear-processed material into interstellar ingredients. It is strange to realize that the star is both dying and fertilizing at the same time. This is the hook, but it is also a trap. Headlines call it the largest star, as if the category was stable and the edge was sharp, like a contest with a fixed ruler. The truth is that largest depends on definition, wavelength, and whether you include the dusty envelope that is actively leaving the star. Photospheric radius is not the same as the outer boundary of the circumstellar dust, and those two can differ by orders of magnitude. A pseudo-photosphere in an optically thick wind can mimic a larger star without changing the core, because the surface is in the wind. A symmetric ejecta can bias measurements, because light from the environment enters the same beam and adds extended brightness. So the superlative is not wrong in spirit, but it is fragile in detail, and detail is where science lives. Distance revisions can move the star up or down the rankings without changing the star itself, which should make any record feel provisional. So the record book is not a crown, it is a snapshot of methods and assumptions, frozen at a moment in scientific history. It is also shaped by what we can observe, because the most extreme stars are often the hardest to measure cleanly. The irony is that the very stars that break our intuition also break our observational shortcuts, forcing more careful definitions. So when we say largest, we should ask, largest by what metric and measured through what veil? And we should ask one more thing. What part of the system is doing the shining, the core, the wind, or the dust? There is historical context behind that reflex to crown a champion. Astronomy has long been drawn to extremes, from the brightest star to the farthest galaxy, because extremes test theory. In the 20th century, as stellar evolution matured, objects like red supergiants became laboratories for late-stage physics. VY-Simmer entered catalogues as a peculiar, variable, very red star, and its surrounding nebula later sharpened its reputation as unusual. As instruments improved, VY-CMA moved in and out of the spotlight, sometimes inflated by early assumptions and sometimes revised downward by better constraints. That back and forth is not embarrassment, it is the scientific process made visible, with a star that refuses to be simplified. Each generation of telescopes adds a layer of clarity, and then reveals another layer of complexity underneath. Correcting the misconception does not reduce the wonder, it sharpens it, because the real story is richer than a single superlative. Even conservative radii still imply a star that would erase the inner solar system, turning familiar orbits into interior space. Even conservative luminosities still imply a star pouring out energy at an industrial scale, every second, for years on end. The real extremity is not a single number, but a system that blurs its own boundary and keeps changing the layer we observe. VY-CMA shows that late evolution can be both inflated and unstable, not merely large, and that instability is measurable. It is a reminder that big is not the only axis of strangeness. Unsteady can be even more revealing. It shows that mass loss is not a footnote, because the star is actively dismantling itself, turning its envelope into a nebula in real time. When we look at the arcs, we are looking at the star's body redistributed into space, like pages torn from a book. That image carries a question that lingers. How much can a star lose and still remain a coherent star rather than a dispersed cloud? At what point does the star become mostly environment, with the core hidden behind its own expelled layers? VCMA sits near that philosophical edge, where identity depends on boundaries that are physically moving. If the boundary is a shifting optical depth, then the star is partly defined by our ability to see into it. We pull back from the boundary and ask what the nebula is really telling us, beyond the fact that it exists. Each knot is a clue to a past eruption, and each arc is a clue to directionality, as if the star favoured certain launch corridors. The outflow is not spherical, so whatever drives it is not perfectly symmetric, and symmetry breaking is a diagnostic. Rotation, magnetic fields, and convection can all break symmetry in different ways, and each would leave a different imprint. Rotation can flatten or bias ejection toward an equatorial plane, while magnetic fields can channel plasma along structured lines. The patterns can overlap too, producing a nebula that looks like layered handwriting rather than a single clean signature. Convection can also do it, because giant cells can create localized upwellings that punch outward more strongly than their surroundings. A companion could also shape ejecta, even if it is faint or hard to confirm, by disturbing the envelope or focusing outflow gravitationally. The environment becomes a forensic scene, where geometry constrains the physics, even when the central engine is hard to observe directly. When we map the nebula's shape, we are mapping forces that acted at the star's surface long ago. That is why the debris is not secondary, it is the evidence. In a way, the nebula is the star's autobiography, written in dust that drifts outward at tens of kilometers per second. Whilst CMA also clarifies why size cannot be separated from environment, because the environment is optically active. Dust both hides and reveals because it blocks visible light and glows in infrared, and those two actions can pull interpretations in opposite directions. That glow can dominate the apparent system, making the star look larger at longer wavelengths, where dust emission is strongest. So the same object can be a dim red point in one band, and a sprawling infrared source in another, with structure that seems to breathe. The star does not change that fast, but our measurement layer does, and that layer is part of the star's outflow. This is why multi-wavelength astronomy is not a luxury here. It is the only way to keep the story honest. In extreme stars, the layer we see is often the layer that is leaving, which means observation is always slightly behind the physics. The photosphere is not a fixed surface like a planet's crust, but a depth in an atmosphere where optical depth reaches about unity. If the atmosphere expands or becomes dustier, that depth moves outward, and the surface follows it like a mirage. So the question becomes less, how big is the star, and more, what physical layer are we calling the star today? VCMA turns that into a practical problem, not an abstract one, because the shifts are large enough to matter. It also turns it into a visual problem, because different images can look like different objects, even when nothing fundamental has changed. This is why VYCMA belongs in the middle of the documentary, where thought experiments must meet stubborn reality. It turns the thought experiment into a tangible case with real data and real disagreement, and the disagreement is scientifically productive. It forces us to separate radius from luminosity, and photosphere from dusty envelope, and measurement from definition. It shows how uncertainty ranges are not excuses, but maps of what physics is hardest, like contour lines around a mountain. It also keeps the central question alive, because the star seems to exceed intuition without breaking rules, and that tension is the point. If a star can be both enormous and ill-defined, then our categories must be flexible enough to describe it. There is a visual rhythm to this lesson, and it mirrors the scientific rhythm. We zoom into a bright core, then we zoom out to a ragged nebula, then we switch wavelengths, and the entire hierarchy shifts. In one view, the star seems compact, and in another it seems to dissolve into its surroundings, as if it cannot hold itself together. Dust lanes become silhouettes, then become glowing filaments, and the same arcs look either like shadows or like embers. That is not just cinematic, it is the observational reality of a hypergiant with an active circumstellar environment. The more carefully we look, the more the boundary becomes an argument rather than a line. And the argument is the story, a star defined by the physics of escape. Now we pivot because VYCMA is extreme and still local. It sits in our galaxy, with our galaxy's metallicity and dust chemistry, and those ingredients matter for how winds work. Metallicity, in astronomical terms, means the abundance of elements heavier than helium, which strongly influences opacity and cooling. More metals generally mean more line opacity and more efficient dust formation, which can strengthen radiation-driven outflows. Lines act like tiny sails for photons, and dust grains act like bigger ones, converting light into outward momentum. So VSEM is a case study under Milky Way conditions, where dust can form readily, and complex molecules can survive in cooler regions. It is a nearby benchmark, a reference point for what extreme looks like when the chemical toolkit is rich. The next mystery asks what changes when the environment changes beyond the Milky Way, where the chemical budget is different. Lower metallicity can alter opacity, dust formation, and wind efficiency in late stages, changing how easily a star can shed its envelope. In some systems, dust can hide the star almost completely, leaving only infrared clues and a faint reprocessed glow. That makes the measurement game harder, because the light we want is filtered through a different kind of veil. So we take what VYCM taught us about boundaries, and we carry it outward, where the same physics plays under altered conditions. If VYCI is difficult with good chemistry and relative proximity, what happens when both advantages are taken away? We leave the Milky Way's familiar chemistry and look for monsters behind thicker veils, where even seeing the star becomes uncertain. And we keep one question in mind because VICMA trained us to ask it. When the boundary is moving, what does it mean to measure size? Transition. VICMA refuses to sit still, and its nebula proves it, with arcs that keep drifting and dust that keeps glowing. Next, we follow that instability beyond our galaxy, where dust and metallicity rewrite the measurement game, and the biggest stars may be the hardest to name. We pivot from a local hypergiant to a nearby galaxy, because environment changes the rules. The Large Magellanic Cloud hangs close by, an irregular satellite of the Milky Way, and it feels almost within reach. On wide-field images, it looks like a detached splash of starlight, a pale cloud set against black, yet it is a whole galaxy. It drifts in the southern sky near the Milky Way's band, bright enough to be noticed without a telescope on dark nights. Its shape is lopsided and restless, with star-forming knots and faint tidal streamers that hint at past gravitational encounters. Those streamers are not decoration, they are gravitational handwriting, drawn by the Milky Way's pull and by earlier close passes. In long exposures, the LMC's outskirts feather into darkness, as if the galaxy is being gently unspooled into intergalactic space. Its stars share a common distance far better than most extragalactic targets, so brightness estimates start on firmer ground. That single advantage matters, because distance is the first rung on the ladder from apparent flux to intrinsic power. In the LMC, we are not constantly renegotiating the scale of the experiment, even when the object itself stays elusive. It also carries a different chemical inventory, with lower metallicity than our galaxy. And that difference is not cosmetic. Lower metallicity means fewer heavy atoms per unit gas, fewer seeds for molecules, fewer ingredients for dust, and fewer spectral lines to catch light. That difference sounds technical, yet it reshapes opacity, cooling, dust formation, and wind strength in ways that change a star's final acts. So the LMC becomes a controlled experiment, where distance is steadier and composition is shifted, and the star must play by altered rules. When we compare an LMC supergiant to a Milky Way one, we're quietly comparing two atmospheres built from different raw materials. The question is subtle, but unavoidable. Does a star die the same way when the periodic table is less available? Metallicity in astronomy means elements heavier than helium, built by earlier generations of stars and dispersed by winds and supernovae. Hydrogen and helium were forged in the early universe, but oxygen, silicon, iron, and the rest were minted later in stellar cores. Those metals are the ash and alloy of cosmic history, and each generation of stars leaves a chemical fingerprint behind. When those metals are scarce, the gas behaves differently, both as a radiator and as a light absorber, so the atmosphere's physics subtly changes. Metals supply many of the spectral lines that absorb photons and transfer momentum outward, especially in hot, ionized winds. Those lines act like countless tiny sails, each catching a narrow slice of the spectrum and converting light into outward push. In plain terms, the star's light finds more handles to grab when metals are abundant and fewer when they are not. This is why metallicity shows up in wind theory as a scaling law, not just as a descriptive label in a catalogue. Metals also help gas radiate energy away, letting outflows cool and condense into molecules and then into dust grains. Cooling is not just a detail. It decides whether an expanding wind stays warm and diffuse or collapses into dense, dusty clumps. In a metal-poor flow, fewer radiative pathways can leave the gas hotter for longer, delaying condensation where dust would normally appear. With fewer metals, the gas can be more transparent in key bands, and winds can change character rather than simply weaken. The same luminosity can drive less mass loss, or drive it differently, depending on which opacity dominates at each layer. Late stellar evolution is not only about mass and age, it is about the chemistry available, and about how that chemistry couples light to matter. Even the dust that finally forms can differ in grain size distribution, which changes both extinction color and how efficiently radiation pressure accelerates it. So metallicity is not one knob, it is a linked set of dials that tune radiation, chemistry, and momentum transfer together. The Large Magellanic Cloud has long served as a calibration arena for astrophysics, from variable stars to supernova remnants. It is close enough that individual stars can be studied in detail, yet far enough that many of them sit at nearly the same distance. Its role in distance work is historical as well as practical, because key-third variables there helped anchor the extragalactic distance scale. Henrietta Leavitt's discovery of the Cepheid period, luminosity relation relied on Magellanic Cloud Cepheids, because their shared distance made the pattern obvious. That insight became a lever for the 20th century, because it turned pulsation into a measuring tape that could reach beyond the Milky Way. When we say the LMC's distance is well measured, we are leaning on decades of cross-checks, pulsating stars, eclipsing binaries, and geometric methods. Detached eclipsing binaries are especially powerful because orbital dynamics and stellar sizes can be modelled to yield a near geometric distance. The method feels almost mechanical. Measure the orbit, infer the stellar radii, compare true brightness to observed brightness, and the distance emerges. That background gives this chapter a rare gift. We can argue about dust and geometry without arguing as much about how far away the object is. Even so, the LMC's lower metallicity keeps whispering that the same stellar type may not behave the same way. If the ingredients differ, should we expect the end-of-life mass loss to follow the Milky Way's template, or to improvise? And if it improvises, what else in our stellar playbook is quietly parochial, tuned to our galaxy's chemistry? In that laboratory sits WOH G64, a red supergiant that refuses to present a clean face. It is not famous because it is easy to measure, it is famous because it is hard, and the difficulty is the point. The defining feature is circumstellar dust so thick that direct starlight is heavily suppressed, as if the star has wrapped itself in smoke. In optical images, the field looks ordinary, yet the star is oddly muted, present but reluctant, like a lamp behind frosted glass. The surrounding sky is sprinkled with other LMC stars, but this one feels like it is dimming itself on purpose. Instead of a simple spherical shell, the dust appears strongly asymmetric in many models, and that asymmetry carries a story. A common interpretation is a torus or disc-like structure, tilted relative to our line of sight, so one side blocks more than the other. The tilt matters because it turns a single object into many possible appearances, depending on which slice of the system we're allowed to view. That geometry turns every basic parameter into a conditional statement, because the star you infer depends on the angle you imagine. In a sense, the dust is not merely in front of the star, it is staging the star, deciding what kind of character we meet. If you cannot see the photosphere cleanly, you cannot read temperature from a simple continuum, because the continuum has been filtered. If you cannot trust the continuum, you cannot apply Stefan Boltzmann without extra assumptions about what surface is actually radiating. If the dust blocks light in some directions and leaks it in others, luminosity becomes angle dependent, not a single universal number. Even the colour of the star becomes suspicious, because reddening can mimic a cooler surface while hiding a warmer one beneath. The same observed redness can be made by a cooler star, or by a warmer star viewed through a thicker wavelength selective curtain of grains. So WHG64 becomes a measurement detective story, not a single headline number, and every clue must be weighed against the others. The mystery is not whether the star is powerful, but how much of that power we are allowed to see directly. And behind that sits a deeper question. Are we measuring a star's body, or the luminous footprint of its own expelled atmosphere? The first clue is the spectrum's energy balance, because the object is infrared dominated, and that dominance is diagnostic. Much of the star's power emerges after dust absorbs it and re-emits it thermally, shifting short-wavelength light into longer wavelengths. That re-emission is not arbitrary. Dust grains settle into temperatures set by radiative equilibrium, then glow like warm embers. Different grains reach different temperatures because size and composition change how efficiently they absorb and radiate across the spectrum. Silicate-rich grains, for example, respond differently than carbon-bearing grains, and their mid-infrared features can betray their identity. In visible bands, the star can look faint and reddened, more like a silhouette than a beacon, because blue light is stripped away first. In the infrared, it brightens dramatically, because warm grains act like a secondary radiator with a broad, smooth spectrum. That shift does not create energy, it redistributes it, and the redistribution is the obstacle because it hides the original stellar fingerprint. When you see the infrared rise, you're seeing the dust respond, and the dust is already a step removed from the photosphere. The star's light has been translated, photons absorbed, energy thermalized, and then released again from a larger, cooler surface. Astronomers build a spectral energy distribution across optical, near-infrared and mid-infrared bands, stitching together many instruments and epochs. They have to be careful with variability, because red supergiants can pulsate, and their dusty envelopes can change on human timescales. A change in pulsation phase can shift the temperature slightly, while a change in dust density can swing the extinction far more dramatically. They ask how much flux is direct starlight, how much is scattered light, and how much is dust emission that has forgotten where it came from. Scattering matters because dust does not only absorb, it can redirect photons, sending a diluted, polarized echo toward us. That echo can make the star seem less extinguished than it truly is, because some of what we see is light that took a detour. They then use radiative transfer models because photons are being absorbed and re-emitted repeatedly, and each interaction depends on wavelength. Radiative transfer is the accounting system for light moving through matter with wavelength-dependent opacity, and it punishes sloppy geometry. It forces geometry into the solution, because a torus does not intercept photons like a sphere, and it does not radiate like one either. So the model must decide where dust sits, how thick it is, how clumpy it is, and how it is illuminated by the star. Even the inner edge of the dust matters, because it is set by sublimation temperature, where grains cannot survive closer in. That boundary creates a cavity, an invisible gap that still shapes the infrared spectrum by controlling the hottest dust temperature. Visualize the system as layered theatre lighting. At the centre is a cool, swollen star, but the stage is ringed by a dusty structure that catches the spotlight and glows back. Along some lines of sight, the dust is a curtain, and along others it is a thin veil, and the difference changes the apparent brightness. A tilted torus means the near edge can eclipse the star's equator, while the far side still shines in infrared as it warms. In that picture, the star and the dust are not separate characters, because each one defines what the other looks like. If the torus is clumpy, then the curtain is stitched with gaps, and those gaps can create flickers of leaked starlight. Those leaks can also carry polarization signatures, subtle orientation cues that hint at the scattering geometry we cannot directly image. This is where radius becomes a moving target again, but in a new way that is almost philosophical. For VSICM A, the boundary was blurred by clumps and arcs in our own galaxy's chemistry, where the photosphere and wind were tangled. For WHG64, the boundary is blurred by a dominant dusty structure that can hide the star itself, then replace it with a proxy glow. A radius inferred from infrared brightness can accidentally become the size of the dust photosphere, not the star's true surface. A radius inferred from a temperature estimate can be wrong if the temperature is dust filtered, because the spectrum has been reshaped, so the same object can be called enormous or merely huge, depending on the assumed geometry, and on which layer you mistake for the star. In the most extreme interpretations, the surface we measure is not gas at all, but an optical depth boundary in dust, an emergent skin made of opacity. WOHG64 has often been cited among the largest known red supergiants in the literature, and that reputation did not appear by accident. That claim is not pure hype, it reflects fits that yield very large radii under certain assumptions about temperature, extinction, and reprocessing. The temptation is understandable, because a dust-dimmed optical source paired with a huge infrared output suggests something extreme is happening, but the claim is also fragile, because the star's effective temperature is model-dependent when the photosphere is not cleanly visible. If the star is warmer than assumed, the required radius drops for the same luminosity, because hotter surfaces radiate more per area. If the dust torus blocks more light than assumed, the intrinsic luminosity must rise to compensate, and the radius can climb again. Each adjustment pushes the inferred radius in a different direction, and the record shifts with it, like a ruler on a moving table. This is why papers can disagree without anyone being careless, because they are often exploring different corners of the same parameter space. The key problem is that the system is not spherical, and largest assumes a single diameter that means the same thing in all directions. A torus introduces viewing angle, and viewing angle changes what fraction of the photosphere is visible at all, even in the near-infrared. It also changes which wavelengths escape most easily, because dust opacity varies with wavelength, and because grain size matters. Small grains are efficient at blocking shorter wavelengths, while larger grains can flatten the extinction curve and alter the colour signature. Grain growth also changes how efficiently radiation pressure can push, because the coupling depends on cross-section and composition. So two observers in different directions would not measure the same apparent star, even if their instruments were identical. We only get one line of sight, so we must infer the rest by modelling and consistency checks, and that is where uncertainty lives. The uncertainty is not just numerical, it is geometric, because the system's true three-dimensional shape is part of the unknown. The LMC's known distance helps, because it removes one common source of disagreement that has haunted many largest star debates. Flux to luminosity conversion is less uncertain when the distance is not being revised repeatedly, and the LMC has been measured with unusual care. Yet the dust geometry reintroduces uncertainty in a different form, through anisotropic extinction and anisotropic emission from the torus. Distance is stable, but the radiative transfer is not simple, and the model becomes the lever that can lift the star's inferred size. It is a strange trade. We gain confidence in where the system is, but we lose confidence in what we are seeing. The galaxy gives us a fixed ruler, while the star gives us a shifting silhouette. Metallicity returns as the deeper theme, because it shapes both the wind and the dust, and it does so through multiple channels. In lower metallicity environments, line-driven winds in hot stars are typically weaker, because fewer metal lines are available to absorb momentum. For cool supergiants, the story involves molecules, dust condensation, and radiation pressure on grains rather than purely line-driven acceleration. Pulsation and giant convection can loft gas outward first, and dust can then form in that lifted material if it cools enough. That sequence matters because dust is not launched from nothing. It needs a dense, cool staging ground where atoms can assemble into solids. Fewer heavy elements can mean fewer raw ingredients for dust, and different grain populations that change how efficiently light can push. It can also alter which molecules form first, shifting the chemistry of the outer atmosphere where dust seeds nucleate. That can reduce the efficiency of dust-driven mass loss, or shift where dust can form, changing the wind structure and timing. So WOHG64 tests whether extreme mass loss can still build an optically thick cocoon when the environment seems to discourage it. If it can, then our intuition about metal poor means dust poor needs qualifiers, because density and dynamics can overwhelm scarcity. If the environment discourages dust, then a thick torus becomes more surprising and more informative, because it implies something must compensate. It could imply a short, intense episode that concentrated material into a dense structure, like a brief storm in an otherwise steady climate. It could imply that even with fewer metals, the star can still manufacture enough dust locally, enriching its own immediate surroundings. That local enrichment would be small on galactic scales, yet enormous in the star's neighbourhood, where density and shielding can accelerate chemistry. It could also imply that geometry matters as much as chemistry, because density can compensate for scarcity when matter is focused. A torus can be optically thick if material is focused into a plane rather than spread widely, raising column density along certain paths. That idea is simple in plain language. Pile the same mass into a smaller region, and it blocks more light. The torus then becomes a physical argument, made visible, an insistence that the outflow was organised, not merely sprayed into space. That focusing raises the question of what shapes the outflow in the first place, because winds do not choose a torus by accident. Rotation can bias mass loss toward an equatorial plane, building a disk-like density enhancement even when the star rotates slowly. Even a modest rotation rate can matter, because the effective gravity is slightly reduced at the equator, making it easier to lift material there. Large convective cells can launch material unevenly, creating preferred directions over time, and those directions can persist as patterns. Magnetic fields can channel plasma, though their role in red supergiants remains debated and difficult to measure directly. A companion could sculpt the flow gravitationally, even if the companion is faint or hidden, and even if it never dominates the light. Binary shaping is a recurring theme in dusty systems, because orbital motion naturally produces spirals, arcs, and equatorial overdensities. Whatever the driver, the dust structure becomes the evidence left behind, like footprints that remain after the walker disappears. And because the dust expands outward, those footprints are time-layered. Older material farther out, newer material closer in. The object we observe is therefore not only a star, but a star plus its processed surroundings, and the surroundings are not passive. The torus is not a separate accessory, it is part of the observable system's identity, because it intercepts and redefines the radiation field. When we say WOH G64 is bright in the infrared, we are partly describing the dust and its temperature distribution across the torus. When we say it is faint in the optical, we are partly describing the same dust, and the way it selectively erases blue light. The star and its environment form a coupled machine that converts spectrum into structure, then structure back into spectrum. In a sense, the torus is a memory device, recording where the wind went and when it was dense enough to become opaque. The memory is imperfect because dust can be destroyed, grains can grow, and clumps can disperse, yet the overall asymmetry can still persist. To reconstruct the central star, astronomers treat the dust as a filter with its own physics, and the filter has tunable parameters. They estimate dust temperature from the infrared peak and from spectral features, because different grain species radiate differently. They infer optical depth from how strongly the optical and near-infrared are suppressed, and from how steeply the spectrum reddens. They test grain compositions because silicates and other species imprint characteristic mid-infrared signatures that act like chemical fingerprints. Those features can include broad emission or absorption bands, whose shapes hint at grain size, crystallinity, and temperature gradients. In some cases, absorption bands suggest we are looking through cooler dust, while emission bands suggest a warmer surface facing us. They vary the torus thickness and inclination, because those control how much starlight escapes directly, and how much is forced into reprocessing. They then ask which combinations reproduce the full spectral energy distribution consistently, rather than fitting only one convenient wavelength. A good fit must also respect physics. Dust cannot be colder than radiative equilibrium allows, and it cannot survive where temperatures exceed sublimation limits. From that modelling, an effective temperature is inferred, but it is never a simple thermometer reading taken from a clean surface. The effective temperature is the temperature of a black body, with the same total emitted flux, a definition that hides complexity behind a single number. In a dust-enshrouded system, the measured flux is already processed, so the inference is indirect and sensitive to assumptions. The model must decide how much of the star's light is hidden and later returned in infrared, and how much escapes as scattered leakage. If that hidden fraction is misestimated, the temperature and radius both shift, and the star's position on the Hertzsprung, Russell diagram, slides. Even the concept of a photosphere becomes layered, because the apparent emitting surface can move outward with wavelength. At some wavelengths, we may be seeing molecular layers above the star, and at others, we may be seeing dust that has become the dominant surface. This layered photosphere is not an exotic exception. It is what happens when opacity is distributed across gas, molecules, and solids. The radius estimate follows from luminosity and effective temperature, but both are entangled with dust, so the calculation sits on uncertain footing. Luminosity depends on integrating the full output across wavelengths, including reprocessed infrared that may dominate the total energy budget. Temperature depends on which part of the spectrum is truly photospheric, rather than scattered or absorbed, and that distinction is model-based. so the radius becomes a derived quantity sitting on top of a layered inference stack, where each layer carries its own degeneracies. Watch G64 is a reminder that even with a known distance, the star can remain partly concealed, and concealment is a physical state. In a sense, the dust does not only hide the star, it creates a new observable object that must be interpreted. The challenge is to keep the bookkeeping straight, what belongs to the star's surface, and what belongs to the star's constructed environment. This is why largest is a tempting label and a dangerous one, because it invites a single ranking where the system resists simplification. A spherical star offers a single radius that most methods can converge on within uncertainties, because the emitting surface is roughly coherent. A torus-wrapped star offers multiple characteristic scales, each tied to a different optical depth surface and a different wavelength regime. There is a gas photosphere, there is a molecular layer, and there is a dust pseudo-photosphere that can dominate the infrared. There is also the torus's outer edge, which can dominate images at certain wavelengths, especially when resolution begins to tease out structure. If we do not specify which layer we mean, we are not measuring the same object, and the debate becomes a semantic fog. The fog is not merely rhetorical, it affects how we compare observations to evolutionary models that assume a more classical stellar boundary. Imagine a sequence of visuals that zoom inward. First, a red point hidden within a faint halo, then a thicker ring that brightens in infrared, then a central source that never fully resolves. At each zoom level, the edge appears in a different place, because the edge is where optical depth approaches one at that wavelength. That is the quiet trick of radiative transfer. What looks like a surface can be a mathematical boundary rather than a solid wall. The boundary is not painted onto the star, it is drawn by the interaction between photons and matter, and it can shift as conditions change. So when we ask for a radius, we are really asking which boundary we are willing to call the star. And when we compare largest objects, we are comparing choices about wavelength, geometry, and what we accept as the emitting surface. G64 therefore extends the documentary's central question in a sharper direction, because it makes the boundary problem unavoidable. How can a star become huge enough to swallow a planetary system if the surface is not unique and may be dominated by expelled matter? What do these extremes reveal about physics, if geometry and environment can manufacture apparent size, and if the star's own wind redraws the map? The answer is that size is partly structure, and structure is partly mass loss, and mass loss is partly chemistry, all braided together. A star can be physically enormous, yet it can also appear larger because its outflow builds a glowing, optically thick envelope around it. We do not just measure stars, we measure star plus outflow systems that rewrite their own boundaries, then dare us to interpret them. The veil becomes a kind of instrument, an instrument made of matter that forces us to read the star indirectly through its consequences. The LMC context makes that lesson more than a local curiosity, because it hints that stellar endings are not uniform across the universe. If metallicity changes wind efficiency, then the late stages of massive stars differ across galaxies, even when their initial masses are similar. That means the population of red supergiants, their lifetimes, and their pre-supernova mass loss can shift in ways that affect what we observe. It also means that the dust they return to their host galaxies can vary in amount and composition, altering future star formation environments. Woke G64 becomes a single data point in a broader argument about galactic ecology, where stars enrich the medium that will form new stars. A galaxy is not only a collection of stars, it is a recycling system, and metallicity is the bookkeeping. When we watch a star bury itself in dust, we are watching the ledger being updated, element by element, grain by grain. The star's cocoon is also a factory for future observations, because it creates its own nebula signature and preserves a time record. Shells and tori store the history of mass loss in geometry and expansion speed, and those speeds can sometimes be inferred spectroscopically. Molecular lines can trace cooler regions, while atomic lines can trace warmer gas, and each one samples a different layer of the outflow. Different layers can correspond to different episodes, as if the star is exhaled in pulses rather than in a single steady breath. They can later interact with a supernova shock, amplifying brightness through circumstellar interaction and converting kinetic energy into light. So the dust is not only a veil, it is a reservoir of energy waiting for a collision, and the collision can rewrite the final light curve. The most dramatic light in a star's life can be shaped by material it shed before it died, which is an unsettling kind of foresight. In that sense, the cocoon is both a mask and a fuse. Quiet now, but potentially decisive when the final explosion arrives. WOH-G64 also forces a practical lesson about how astronomy works when direct light is blocked, because we must become indirect observers. We rely on infrared because it penetrates dust and because dust itself radiates there, turning obscuration into a new signal. We rely on models because the system is not resolved into simple layers by most instruments, and because the geometry is not symmetric. We rely on consistency across wavelengths, because any single band can be dominated by the wrong component, dust, scattering, or photosphere. We accept that the answer is a family of solutions, constrained by data but not unique, and we learn to speak in ranges. That is not indecision. It is the honest shape of inference when nature hides the center. The discipline is to keep asking what would change if the torus were thicker, clumpier, or tilted by a few more degrees. This is not a weakness. It is the correct response to a system that is genuinely three-dimensional and time-evolving. A torus is a statement that symmetry is broken, and broken symmetry demands more parameters, from inclination to density gradients. More parameters mean more degeneracies, unless we add more kinds of data to break them, and each new dataset is a new lever. So the next step is not only better telescopes, it is better constraints on geometry and dust physics, and better ways to connect them. Interferometry in the infrared, polarimetry, and high-resolution spectroscopy each attack a different ambiguity, and together they triangulate. Polarization can reveal scattering angles, interferometry can hint at spatial scales, and spectroscopy can trace velocities and molecules. When those methods agree, the veil becomes less of a wall and more of a map, with contours we can begin to trust. When they disagree, the disagreement is informative too, because it points to missing physics in grains, clumping, or time variability. The mysterious tone is earned here, because the star is partly hidden by its own making, and the veil is not static. We are not looking at a clean sphere, we are looking at a luminous engine behind a constructed screen, and the screen has texture. The screen is made of the star's own expelled matter, shaped by forces we are still disentangling, and perhaps by episodes we did not witness. So the object's identity is distributed across space, and the boundary is an evolving radiative surface rather than a simple edge. In a quiet way, WOH-G64 asks a thought-provoking question. When a star hides behind its own wind, what does it mean to see it? Is seeing the direct photosphere the only kind of seeing, or can the dust glow be treated as a truthful shadow of the engine behind it? We step back and connect the chapter to the documentary's conclusion theme, because this case clarifies the broader pattern. At the far end of stellar evolution, bigger is never one number, and WOH-G64 makes that literal with dust-defined surfaces. Radius, luminosity, mass and environment weave together, and geometry decides what we can see and what we must infer. By measuring the veil, we learn about the engine, and by measuring the engine, we learn why the veil exists and why it is shaped. The monster is not only the star, it is the coupled system that blurs the star's edge, then glows with stolen light, and in another galaxy, under another chemistry, that coupled system becomes a test of our models and of our assumptions about how stars end. Now we turn the page because red supergiants and hypergiants are about enormous radii and cool light. The title of this documentary also hints at unimaginable brightness. Not only swollen size and brightness brings its own boundary problems. To reach that regime, we leave bloated cool stars and enter ultra-hot, ultra-massive stars, where photons push harder than intuition expects. There, the boundary problem returns in a new form, driven by radiation pressure and violent winds, and the veil becomes a storm. We turn the page from swollen, cool giants to hot stars that weaponize light. The central question sharpens here, because the physics becomes almost confrontational. How can matter keep falling inward when photons push outward, and when the star's glare is already a force? In the cool supergiants, size was a kind of illusion, an atmosphere stretched thin, a boundary softened by molecules and dust. Here, the illusion flips, and the star can be compact in radius, yet violently dominant in power. The camera language changes with it, because the threat is no longer contact. The threat is exposure, radiation that reaches far beyond any visible edge. The Tarantula Nebula, also called 30 Doradus, sits in the Large Magellanic Cloud as a starburst engine. From a distance it looks like a single glowing patch, but close in it becomes a landscape. Filaments knot into ridges, cavities open like torn fabric, and bright rims trace where radiation meets colder gas. Dark lanes of dust cut across the glow like ink in water, and the brightest knots feel almost overexposed. It is not one nursery, but many, layered in molecular gas, dust lanes, and ionized bubbles. The ionized regions shine because electrons recombine with protons, releasing photons in familiar lines. Hydrogen's red H-alpha glow becomes a map of where ultraviolet light is actively rewriting chemistry. In the same frames, oxygen and sulfur lines add greens and golds, hinting at temperature and density changes within the storm. Ionization is not just a colour, it is a state change that reshapes the gas. When ultraviolet photons strip electrons away, the gas heats to around 10,000 Kelvin and pressure rises. That pressure drives expansion, and expansion sculpts the cavities we see as hollowed shells. The nebula's structure becomes a record of energy injected over only a few million years. Its scale is deceptive, because our eyes want to frame it as one nebula. It is a single region that rivals entire galaxies in star formation intensity. In astrophysical terms, it behaves like a miniature starburst galaxy, embedded inside a nearby companion. The light is so intense that even the surrounding interstellar medium is pushed into arcs and curtains. The Large Magellanic Cloud matters because it is not the Milky Way. It is smaller, less chemically enriched, and shaped by interactions with its neighbours. That difference becomes a laboratory variable, not a footnote. The LMC's orbit and tidal history have stirred its gas, and 30 Doradus sits where that gas can pile up and ignite. This is where environment stops being background and becomes a controlling parameter. The LMC's lower metallicity changes opacity, cooling pathways, and wind strength across stellar lifetimes. We carry forward the earlier lesson because every extreme number depends on what the light passed through. Even the dust that dims a star also tells us what the galaxy has been able to manufacture. Metallicity sounds abstract, but it is simply the fraction of matter made of elements heavier than helium. Those elements provide extra electrons, extra spectral lines, and extra ways for gas to radiate energy away. With fewer heavy elements, gas can cool differently, and stars can drive winds differently. In plain terms, fewer metals can mean less efficient braking by radiation, and that changes how long a massive star can stay massive. Cooling matters during collapse because hot gas resists compression. Heavy elements and dust grains radiate energy through many transitions, letting clouds shed heat and fragment. With lower metallicity, fragmentation can shift, and the typical masses that form can change. That does not guarantee bigger stars, but it changes the rules of the competition. Historically, 30 Doradus became famous because it forced astronomers to confront scale. Early photographic plates showed a bright, irregular glow in the southern sky, but the true complexity emerged with spectroscopy and space-based imaging. Over decades, it shifted from a pretty nebula to a benchmark for massive star physics. Each new telescope generation turned a cloud into a layered ecosystem of shocks, ionization fronts, and clustered births. At the heart of 30 Doradus is R136, a dense cluster packed into a small volume. In wide-field shots, it is a glittering knot inside a storm of gas. In close-up, it becomes almost uncomfortable. Stars stacked on stars, light overlapping light. Diffraction spikes cross and recross, and the background refuses to go dark. Crowding is not a detail here. It is the condition that allows the most massive stars to form quickly, because gas is abundant and gravity has many ways to concentrate it. The cluster is young enough that its brightest members have barely had time to drift apart. The stellar density is so high that close encounters are not rare events. They are part of the cluster's everyday physics. Youth matters because massive stars live fast. They reach the main sequence while still embedded in their birth environment, and they begin altering that environment almost immediately. In R136, the usual separation between formation and feedback collapses. The same objects that are still finishing their growth are already blasting the nursery with ultraviolet light. R136 is a pressure cooker for stellar evolution, and the pressure is not metaphorical. Gas densities, radiation fields, and gravitational interactions all rise together, Massive stars ignite fast, burn fast, and rewrite their surroundings with ultraviolet radiation. Even the cluster's gravity helps trap gas long enough for feedback to become a complex, tangled conversation. Their light carves ionized bubbles and drives shocks that can trigger or suppress nearby collapse. A shock front can compress a cloud edge, tipping it toward gravitational instability. The same radiation can also heat gas, raising pressure and preventing collapse. Star formation becomes a pattern of yes and no written in the same breath. In this cluster, feedback is immediate, and the timescales are brutally short. A few 100,000 years is not a long time in astronomy, but it is enough for ultraviolet light to excavate cavities. It is enough for winds to sweep shells and for turbulence to thicken the chaos. The nebula looks ancient, but many of its sharp edges are younger than the first human cities. We have been chasing largest by radius, where cool temperatures inflate surfaces into fog-like boundaries. Now we chase a different extreme, where temperature and luminosity dominate the story. Here the monster is not the widest sphere. It is the most luminous furnace per unit surface area. The metric shifts from how far the star reaches physically to how hard it pushes energetically. The visuals should feel harsher here. The palette shifts toward electric blues and stark whites, where ionized gas glows and dust silhouettes cut across the light. The nebula becomes a battlefield of illumination, with shadows that look carved rather than cast. In motion, the camera can linger on bright rims where ionization fronts wrinkle like shorelines. R136A1 enters as a symbol of that regime. It is often discussed as a hydrogen-rich wolf, Rayet-type star in the WNH category. It is not the stripped, dying wolf, Rayet stereotype from older textbooks. It is a very massive star still burning hydrogen, already showing wolf, Rayet-like winds. That already is the unsettling part because it suggests the atmosphere is extreme from the start. That classification carries history. Wolf, Rayet stars were first identified in the 19th century by their broad emission lines, which looked nothing like ordinary stellar spectra. Only later did the connection become clear. Those lines are signatures of dense, fast outflows. The spectra were not just labels, they were early evidence that some stars are wrapped in their own escaping gas. In WNH stars, hydrogen remains visible in the spectrum, which signals a different evolutionary meaning. The star can be near the beginning of its life, not the end. It is a reminder that spectral appearance can reflect an atmosphere in motion, not a core that is exhausted. The star's type becomes a snapshot of wind physics, not a simple timestamp. Its luminosity is on the order of millions of solar luminosities, depending on models and assumptions. That number is not just brightness, because luminosity is energy per second. It is the rate at which nuclear binding energy is being converted into radiation and particle motion. In practical terms, it is a power output so high that the surrounding gas cannot ignore it. Its initial mass has been estimated well above 100 solar masses, with cited values reaching roughly 200 to 300. Those numbers are not trophies, they are stress tests for the physics that sets an upper limit. They also force us to ask whether a star is always a single object, or sometimes a blended system wearing one name. If the mass is truly that high, the interior is not a scaled-up sun. The core becomes dominated by radiation pressure, and the temperature sensitivity of nuclear reactions becomes extreme. Even small changes in structure can change how energy moves outward. Convection, radiation, and turbulent mixing become competing routes, and the star's stability depends on their balance. The first trap is the word big, because it invites the wrong comparison. A red supergiant can be physically larger in radius and still be dimmer in total power. A hot compact star can outshine it by orders of magnitude because temperature drives flux so strongly. The eye wants diameter, but physics demands energy. Stefan, Boltzmann is still the quiet engine behind the drama. Luminosity scales with surface area and with temperature to the fourth power. Raise the temperature modestly and the emitted power climbs brutally fast. A doubling of temperature is not a gentle change, it is a 16-fold jump in radiated flux, so the hottest stars do not need enormous radii to dominate the energy budget. Their photospheres can be comparatively small, while their ultraviolet output is overwhelming. The thought experiment changes, because the danger zone expands far beyond the star's physical edge. The habitable distance becomes a meaningless phrase under that kind of ultraviolet flood. Instead of being swallowed by a bloated surface, Planets are erased by radiation and wind long before contact. Atmospheres are heated, molecules dissociate, and atoms are ionized into plasma. Even rock is not safe if the irradiation is intense enough. The star's photons can drive atmospheric escape the way a furnace drives steam from water. That shift reframes the documentary's hook. Swallowing the solar system is not only about radius, it is also about influence, because influence is what the star can do to space around it. We are measuring reach in momentum and ionization, not in kilometers. A star can be too compact to engulf Jupiter, and still sterilize and strip everything out to many astronomical units. The star's reach becomes a sphere of ionization and momentum, not a sphere of gas. The boundary becomes an effect, not a surface. In the visuals, the edge is drawn by glowing fronts and expanding shells, but nature seems reluctant to allow unlimited brightness. The deeper we go into R136, the more we feel a ceiling, as if the cluster is pressing against a rule. The ceiling is not set by imagination, it is set by the momentum of light. When photons become numerous enough, they stop being messengers and start being muscle. Radiation pressure is simple in concept and ruthless in consequence. Photons carry momentum, and when they are absorbed or scattered, they push. In everyday life, that push is tiny, but in a star it becomes a structural force. It is the same principle used in solar sails, scaled up until it can peel a star's skin. In ordinary stars, gravity dominates and radiation pressure is a supporting actor. In ultraluminous stars, radiation pressure becomes central to hydrostatic balance. The star's outer layers are held together by a compromise between inward weight and outward light. The compromise is not static because the star's output and opacity change with depth. The Eddington limit formalizes the balance in a clean, almost elegant way. It is the luminosity where outward radiative force on matter matches inward gravitational pull. The limit depends on opacity, which depends on what the gas is made of and how ionized it is. In its simplest form, it assumes electron scattering dominates, which is a useful baseline even when reality adds complications. Opacity is the coupling between light and matter, and it determines how easily photons transfer momentum. If gas is more opaque, photons interact more often, pushing more effectively. Change metallicity, change opacity, change the effective ceiling. That is why a galaxy's chemical history can quietly rewrite a star's fate. At or near this limit, a star becomes a negotiation between light and weight. If luminosity rises, the outward push rises with it. If the push approaches gravity, the outer layers become easy to unbind. The star is not exploding, but it is perpetually close to shedding what it cannot hold. The star can still exist, but it pays a price in mass loss. It also becomes vulnerable to instabilities, because small fluctuations can tip a layer over the balance. The surface becomes less like a wall and more like a weather system. Brightness variations, clumps and shocks become the visible symptoms of a deeper tug of war. This is where the boundary problem returns in a new form. For red hypergiants, the boundary blurred because of dust and extended atmospheres. For R136A1, the boundary blurs because the wind is so dense and fast that the photosphere can sit inside outflow. The star's surface is not where gas stops, it is where light last struggles free. The surface can be a layer in a moving storm, defined by optical depth rather than solid matter. If the wind thickens, the apparent radius can shift outward. If the wind thins, the photosphere retreats inward. The star's measured size becomes a property of the wind as much as the core. The winds are not gentle, they are fierce, persistent, and driven by radiation itself. They strip mass, reshape evolution, and limit how long the star can remain ultra-massive. The star is bright because it is massive, and it sheds mass because it is bright. That feedback loop is the brightness limit expressed as behavior. In visual terms, imagine a star trying to hold onto itself while blasting its own atmosphere away. The outflow is invisible in ordinary light, but spectroscopy reveals it as broadened lines and shifted absorption. The wind becomes a measurable speed, not a poetic idea. Line profiles turn into velocity maps, and velocity maps turn into mass loss estimates. Mass loss in hot stars is often line-driven. Metal ions provide many spectral lines that absorb photons in narrow wavelength bands. Each absorption transfers momentum, accelerating gas outward, and repeated interactions build a sustained flow. In effect, the star's spectrum becomes a ladder that gas can climb out of the gravity well. The more line opacity available, the more efficiently light can push. That is why heavy elements matter even when they are rare. A small abundance can dominate the momentum budget because the number of available transitions is large. In a hot atmosphere where many ions exist at once, the line list becomes a dense forest. This is where metallicity becomes destiny. In lower metallicity environments, there are fewer metal ions to provide line opacity. Winds can be weaker for the same luminosity, allowing stars to retain more mass for longer. That can make the upper mass question sharper in the LMC than in the Milky Way. It also means the same star could evolve along a different track if it formed in a richer galaxy. Yet the story is not one-dimensional, because nature has multiple ways to couple light to gas. Even with weaker line driving, extreme luminosity can still push matter through electron scattering. Free electrons act like tiny mirrors, scattering photons and feeling their momentum. That coupling is simpler and more universal, because hydrogen and helium provide electrons almost everywhere in these hot layers. There are also opacity features that appear at specific temperatures, where certain ions change their electron configurations. Those changes can create local bumps in opacity, which can destabilize layers. The Eddington concept is global, but instabilities can be local. A star can be globally stable, while parts of its atmosphere behave like boiling water. Layers can flirt with the limit even if the whole star is not exactly at it. A region deep in the atmosphere can become super Eddington for a moment, then vent energy through clumps and shocks. The wind can become structured, not smooth. Clumping matters because it changes how light threads through the outflow, and it changes what our telescopes infer. Wolf, Rayet-like behavior in WNH stars reflects that tension. Strong winds can mimic the spectral signatures of a later evolutionary stage. The star can look evolved because its atmosphere is being peeled and accelerated, not because its core has finished hydrogen burning. The label is a warning that appearance and interior age can diverge. Classification becomes a clue to physics, not a simple age label. The spectrum is a report from the wind, and the wind is a report from the luminosity. In R136A1, the atmosphere is effectively an experiment running in real time. The star is telling us how close it is to the edge by how violently it sheds itself. R136A1 therefore sits at a crossroads in our narrative. It is an object that forces us to connect mass, luminosity, opacity, and environment in one equation. It also forces us to admit uncertainty, because the most extreme stars are the hardest to measure cleanly. The closer we get to the limit, the more measurement becomes part of the physics. The cluster is crowded enough that light blends. A single bright source can hide multiple stars inside one point spread function, especially when the background is bright and structured. In a dense core, even space telescopes face confusion. The eye sees one beacon, but the reality may be a tight group whose light is braided together. Unresolved binaries can masquerade as a single ultra-massive star. If two massive stars are blended, the inferred luminosity rises, and the inferred mass can be inflated. The error is not trivial, because mass estimates climb steeply with luminosity in this regime. A modest luminosity bias can translate into a dramatic mass claim. This is not a minor correction. The existence of a true 200 to 300 solar mass single star is a different claim than a tight pair. The upper mass limit depends on which is true, and the theoretical implications diverge. One scenario challenges formation physics, while the other challenges our ability to separate crowded light. If the object is multiple, then nature may still enforce a lower cap for single star formation. If it is single, then the cap is higher, or the formation pathway is more creative than we assumed. Either way, the cluster becomes a test of our confidence. It asks whether the ceiling is real, or whether our measurements are simply brushing it. Astronomers attack this with spectroscopy and high-resolution imaging. Spectral lines can reveal Doppler shifts from orbital motion, or composite features from two temperatures. Imaging with space telescopes and adaptive optics can separate close companions in favourable cases. Time becomes a tool as well, because repeated observations can catch periodic motion. Even then, crowding and brightness contrast keep the problem alive. A faint companion can hide in the glare, and a nearly equal companion can mimic a single spectrum. The best observations reduce uncertainty, but they rarely erase it. The cluster's own nebulosity adds another veil, because emission lines from gas can overlap stellar features. The uncertainty is part of the theme. We are not only asking what nature builds, we are asking what our instruments can disentangle in a starburst core. The measurement problem is not an obstacle to the story. It is the story, because limits depend on what is real. There is also the question of models, because massive star atmospheres are not simple. Winds are clumpy, and clumping changes how we infer mass loss rates from emission lines. If the wind is more structured than assumed, the derived parameters can shift. A clumped wind can produce strong emission with less total mass, which means the star may be losing less than a smooth model suggests. Temperature estimates depend on how we interpret ionization balances in the spectrum. Luminosity depends on distance extinction and bolometric corrections, especially in the ultraviolet. Each step is careful, but each step carries assumptions. Even the extinction law in the LMC can differ from the Milky Way's, and that difference can bend the inferred energy output. Now we return to formation, because even a confirmed mass is only half the puzzle. How does a star get that massive without stopping its own growth? As soon as a protostar becomes luminous, its radiation heats and pushes surrounding gas. The paradox is immediate. The brighter the protostar becomes, the more it should sabotage its own supply line. The fuel supply should be disrupted at the very moment it is needed most. In the simplest picture, radiation pressure on dust would halt accretion by reversing the flow. Yet massive stars exist, so the simplest picture is incomplete. The universe is telling us that geometry, turbulence, and time dependence matter. One pathway is accretion through disks, which changes the geometry of the problem. A disk can channel material inward while allowing radiation to escape preferentially along the poles. The geometry reduces the effective feedback on the inflow. Instead of pushing equally in all directions, the star's light finds the easiest exit. In that scenario, bipolar outflows carve cavities, and those cavities act like exhaust vents. Photons escape more easily along low-density directions, while dense gas continues spiraling inward. It is not a guarantee, but it is a loophole that nature can exploit. The visuals can show a bright conical glow above and below a darker disk, like a lighthouse beam through fog. Another pathway is fragmentation and competitive accretion in dense clusters. In a crowded environment, gas flows can be redirected by gravity toward the deepest potential wells. The most massive protostars can sit at the center and keep feeding. The cluster's gravitational field becomes a conveyor belt, steering gas inward along filaments. The cluster becomes a funnel, not a collection of isolated berths. Gas that might have formed many moderate stars can instead be captured by a few central objects. The distribution of mass becomes a dynamical outcome, not a simple initial condition. In this view, who becomes massive depends on where you sit in the gravitational landscape. A third pathway is mergers, which becomes plausible when density is extreme. In the densest cores, close encounters can harden binaries and drive collisions. Two massive stars can merge into one, producing an object that appears to violate simple accretion limits. The merger route feels violent, but R136 is one of the few places dense enough to make it conceivable. If mergers happen, the upper mass limit is not only a formation limit, it becomes a dynamical outcome of crowding, where gravity and chance encounters sculpt the final roster. The cluster becomes a machine for building extremes. The same environment that confuses our measurements may also be the environment that creates the extremes we measure. Each pathway leaves different fingerprints, and those fingerprints are what observers look for. Disks imply outflow cavities and angular momentum signatures. Competitive accretion implies mass segregation and gas inflow patterns. The questions are subtle, because young clusters can rearrange quickly, and cores can masquerade as consequence. Mergers imply rapid rotation, chemical mixing, and possibly transient outbursts that briefly brighten the cluster. A merged star can be more homogeneous, with fresh hydrogen mixed inward. That mixing can extend hydrogen burning and alter the star's later appearance. It can also change the wind, because surface composition affects opacity and therefore momentum transfer. R136 is one of the few places where all of these ideas can be tested against a real population. The cluster's youth means we are close to the initial conditions. The density means interactions are plausible, not just hypothetical. The result is a living laboratory, where formation and evolution overlap in the same crowded frame. The LMC distance means we can compare many stars at a shared scale. We are not guessing distances star by star across the Milky Way's dust. We are looking at a population that sits essentially at one known range. That shared distance turns relative brightness into a more trustworthy clue about relative power. But the physics that tries to stop growth never disappears. Radiation pressure rises as luminosity rises, and luminosity rises steeply with mass for massive stars. The star approaches the Eddington balance as it grows, and the wind becomes the safety valve. The closer it gets to the limit, the more insistently it vents mass to stay below it. The star can still gain mass, but it leaks mass at the same time. Accretion becomes a race against self-driven erosion. The question becomes whether the inflow can outpace the outflow long enough to build the core. In that race, the environment matters, because dense gas can deliver mass faster than a sparse cloud ever could. This is the brightness limit as a narrative engine. It is not a hard wall where stars cannot exist. It is a regime where stability is expensive and where the star must continuously shed matter to remain bound. The limit is felt as a constant tax paid in wind. The monster survives by eroding itself, and that erosion is not gentle. The wind carries away angular momentum and chemical products from the surface. Over time, the star's identity changes, even while it remains recognizably the same object. It is like watching a mountain in a storm, where the shape persists but the surface is always moving. The wind also changes what the star will become. Mass loss strips the envelope, changes the core-to-envelope ratio, and alters the path across the Hertzsprung, Russell diagram. It changes whether the star will become a classical wolf, Rayet star later. It also changes how long the star spends in each phase, because losing mass can expose hotter layers and intensify the feedback. It changes how much mass remains for the final collapse. That remaining mass influences whether the end is a supernova, a direct collapse, or something more exotic within the same family of outcomes. The wind is not decoration, it is destiny. Even the star's final explosion, if it has one, will be shaped by what the wind has already removed. The wind changes the environment too. It injects momentum and enriched material into the nebula, and it pre-shapes the circumstellar medium. That medium will matter at death, because any explosion will crash into it. A blast wave hitting a dense shell is not the same as a blast wave expanding into emptiness. The star writes the conditions of its own finale in advance. Shells and bubbles become the stage, and the final event becomes the performance. Even before the end, the star is already arranging the scenery. The nebula's arcs are not background art, they are the star's autobiography written in gas. We connect back to earlier chapters. VY Canis Majoris and WOHG64 taught us that surface can be a moving optical depth layer. ARM136A1 teaches the same lesson under opposite conditions. One boundary is cool and dusty, the other is hot and ionized, yet both refuse to be a clean line. In hot stars, the moving layer is not dust and molecules. It is ionized gas accelerated by light. The boundary is defined by where photons last scatter, and that location can ride outward on a wind. When we say radius, we are really naming a depth where the star becomes transparent enough to be seen, and we connect back to the documentary's conclusion theme. Bigger is never one number, and here the numbers fight each other. A star can be compact in radius, extreme in mass, and almost absurd in luminosity. The same object can be smaller than a red supergiant and still dominate an entire region's energy budget. Environment and metallicity decide how strongly light couples to matter, and therefore how long the monster can persist. The same star placed in a different galaxy would not live the same life. It would not lose mass at the same rate, and it might not even look the same. That is a quiet reminder that a star is not only a self-contained engine, it is also a product of its chemical neighborhood. The stakes rise because the upper mass question is also a cosmic history question. If low metallicity galaxies can grow and retain more massive stars, then the early universe may have hosted even more extreme objects. Those stars would have poured ultraviolet light into young galaxies. Their radiation would have been a major ingredient in changing the universe from neutral fog to transparent space. They would have driven reionization and chemical enrichment, changing how later generations formed. In that sense, the brightness limit becomes a lever on cosmic evolution. A local star in the LMC becomes a proxy for ancient conditions. When we study R136A1, we're also studying a faint echo of the first stellar eras. Still, we keep our footing. R136A1 is not a single clean data point. It is a best-studied representative of a class, embedded in crowding and shaped by model assumptions. The more extreme the claim, the more carefully we have to interrogate every step that produced it. Its mass estimate depends on atmosphere models, wind clumping, and how we translate spectra into temperatures and luminosities. Extinction corrections matter, because dust and gas absorb and scatter light along the line of sight. Even small errors can propagate into large inferred differences. The star's true ultraviolet output is partly hidden from our eyes, which means we reconstruct it through models rather than direct sight. The uncertainties are not embarrassing. They are the boundary of current knowledge, and boundaries are where science is most alive. They tell us which measurements matter next, and which assumptions deserve suspicion. They also remind us that nature does not owe us clean experiments, especially not in the most crowded cluster cores. We end this chapter with the tension unresolved on purpose. Nature can build stars that approach the brightness limit, and perhaps exceed naive expectations. Light can fight gravity and still lose, but it extracts payment in mass loss and instability. The star remains luminous, but it cannot remain unchanged. The question becomes unavoidable, because the end is already present in the beginning. If a star can live this bright, how does it die? What does it leave behind when the wind finally cannot pay the bill? And when that bill comes due, does the surrounding nebula amplify the finale or absorb it? Transition. We leave the tarantula's crowded core with one thought. The brightest stars do not merely end, they detonate into environments they already sculpted. Transition. We leave the tarantula's crowded core with one thought. The brightest stars do not merely end, they decide what the next universe can be. Our central question has been about size and power, and about boundaries that refuse to stay put. In the final act, the boundary problem becomes a fate problem. What counts as an ending when the surface is a wind? The camera lingers on a star whose edge is a moving frontier, where gas is lifted, cooled, and blown away. Even in still images, the star looks unfinished, as if it is continuously rewriting itself. Massive stars live fast because their cores run hot, and their luminosities are extreme. Their central temperatures climb high enough that nuclear reaction rates respond like a switch, rising steeply with even small increases. The fuel reservoir is larger than the Sun's, yet the burn rate rises even faster. A star with tens to hundreds of solar masses spends only a few million years shining. It trades longevity for pressure support, and it pays with speed. That short lifetime is not a footnote, because it links monsters to their birthplaces. They die near the clouds that formed them, still inside the feedback they created. Their ultraviolet light has already carved cavities in the nebula, and their winds have piled gas into bright rims. Their deaths are not isolated fireworks, they are events inside a living galaxy. When we watch a supernova in a star-forming complex, we are watching a local ecosystem react. The interior story is a ladder of fusion stages that accelerates as the core evolves. Hydrogen fuses to helium, then helium to carbon and oxygen, and the core contracts again. Each contraction raises temperature and density, unlocking the next reaction channel. The star becomes an onion of shells, each burning a different fuel. In cross-section, the layers resemble nested storm systems, distinct, yet coupled through pressure, mixing, and gravity. Hydrogen burning, for most of the star's life, is governed by the CNO cycle in very massive stars. Carbon, nitrogen, and oxygen act as catalysts, letting hydrogen fuse efficiently at higher temperatures than the Sun's core. That efficiency is a gift and a curse, because it supports a huge luminosity while draining the fuel faster. Convection often dominates the core, stirring fresh hydrogen inward and carrying helium outward. The star's interior is not calm, it is boiling, churning, and constantly rearranging composition. Helium burning begins when the core contracts enough to ignite the triple alpha process. 3 helium nuclei combine in steps to build carbon, and additional reactions can add helium again to form oxygen. These reactions are sensitive to temperature, so the core self-regulates through expansion and contraction. Meanwhile, the outer hydrogen-burning shell continues, adding helium ash onto the core. The star is building its own pressure cooker, layer by layer. Carbon burning follows, then neon, then oxygen, then silicon. Each stage yields less energy per unit mass than the one before, and each stage runs for a shorter time. Hydrogen burning can last millions of years, while silicon burning can last days. The monster's clock speeds up as it approaches the end. The visual rhythm changes too. Long, steady eras give way to rapid, unstable episodes. The reason is simple and brutal. Radiation losses rise and the core must burn faster to hold itself up. At advanced temperatures, the core produces vast numbers of neutrinos through thermal processes and weak interactions. Neutrinos become a dominant cooling channel in advanced stages, carrying energy away almost without interaction. They slip through the star as if it were transparent, taking pressure support with them. The core becomes a furnace with an open drain. In these late stages, burning is almost a misleading word because the timescales become so short. Silicon burning does not simply fuse two nuclei into a heavier one, but cycles through a network of reactions. Photons at extreme energies can break nuclei apart, and the fragments recombine into ion group elements. The core is approaching nuclear statistical equilibrium, a state where composition is set by temperature, density, and binding energies. The star is no longer choosing reactions. Physics is choosing for it. Then the ladder stops at iron. Iron is the end of the energy bargain, because fusing iron does not release energy. Iron group nuclei are already near the peak of binding energy per nucleon. Past this point, fusion costs energy instead of paying it. The star can still rearrange matter, but it cannot profit from it. So the core becomes a loaded structure that cannot earn its own support. It grows as silicon burning piles iron group ash into the center. The mass of this iron core is not arbitrary, because it is constrained by electron degeneracy pressure and by temperature. When the iron core crosses a stability threshold, pressure support fails rapidly, gravity takes over, and the monster's last act begins. Collapse is not a gentle inward drift, it is a runaway. Electrons are squeezed into protons, producing neutrons and a flood of neutrinos. This electron capture reduces the number of electrons available to provide degeneracy pressure. It also changes the core's composition while it falls, turning a hot plasma into neutron-rich matter. In a fraction of a second, the core's identity shifts. As density rises, the core becomes opaque to neutrinos for a brief window. Neutrinos that once escaped freely begin to scatter, and their energy becomes trapped in the collapsing matter. The infall speed climbs to a significant fraction of light speed, and the core's inner region collapses almost as a single unit. The outer layers lag behind, still falling inward like a collapsing building. The star is imploding under its own weight. At nuclear densities, the inner core stiffens and rebounds, launching a shock. That shock initially moves outward, but it loses energy by breaking apart heavy nuclei and by radiating neutrinos. Photodisintegration is especially costly because it consumes energy to split iron into lighter particles. In many models, the shock stalls, hanging in a precarious balance. The question becomes whether it can be revived. Neutrinos are the strange protagonists here. They carry away most of the gravitational binding energy released in collapse, roughly 1053 ergs in a typical core collapse event. Only about 1% of that energy needs to couple to the surrounding material to power a visible supernova. A small fraction, deposited behind the stalled shock, may be enough to drive an explosion. The mechanism is still an active frontier, not a closed case. Modern simulations show why the problem is hard. Convection and turbulence behind the shock can keep matter in the heating region longer, increasing neutrino absorption. The standing accretion shock instability can slosh the shock back and forth, changing the geometry of the flow. Rotation and magnetic fields can add still more complexity, sometimes launching jets in extreme cases. The explosion, when it happens, is not necessarily spherical. It can be lopsided, directional, and messy. This is where competing endings emerge, and we keep the mystery intact. Some monsters die as brilliant core collapse supernovae. Some die as partial eruptions that repeat. Some may die with almost no light at all. The same basic physics, gravity versus pressure, can resolve into different outcomes depending on structure and history. For red supergiants and hypergiants, the classic expectation is a core collapse supernova. The envelope is extended and loosely bound, so an explosion can unbind it efficiently. The result can be a Type II supernova, often with hydrogen signatures. Yet even here, the details depend on mass loss and structure. A star that has shed much of its hydrogen may shift toward a different spectral class, changing what we call the event. The visuals of a red supergiant's envelope help explain why it is vulnerable. The outer layers are cool enough for molecules and dust to form, and their densities can be low enough that radiation pressure and pulsations matter. The star's photosphere can sit far from the core, like a thin skin stretched over a vast volume. When the shock reaches that skin, it can produce a brief flash as it breaks out. Then the expanding debris cools, recombines, and glows for months. We call back to the earlier boundary problem because it now shapes the light curve. If the star built a dense circumstellar medium through episodic ejections, the shock will collide with it. That collision converts kinetic energy into radiation, sometimes producing an unusually bright event. The size of the system becomes the size of the stage. The supernova is not only a blast, it is a crash into the star's own past. The circumstellar medium is not just empty space with a little gas. It can be a structured landscape of shells, arcs, and dusty knots, each with a different density and velocity. When the shock plows into a dense region, it decelerates, heats, and radiates strongly. Narrow emission lines can appear, signaling slower moving gas being ionized by the collision. In extreme cases, interaction can dominate the brightness, turning the supernova into a sustained conversion of motion into light. VY Canis Majoris and WHG64 were not just measurement puzzles, they were pre-explosion environments. Asymmetric arcs, tori, and clumps become targets for the shock. The final brightness can be amplified or muted by material shed centuries earlier. The monster writes its own finale in advance. Even the dust it made in life can shape the colours we see in death. There is also a timing element that makes these environments haunting. A shell ejected 1,000 years before collapse may sit at a radius the shock reaches weeks after explosion. Another shell, thrown off in a last convulsion decades earlier, may be struck within days. The light curve can therefore carry a kind of stratigraphy, a layered record of the star's last centuries. We read that record indirectly, through brightness changes and spectral evolution. But not all massive stars end as standard core collapse explosions. At higher masses, the core conditions can trigger pair instability effects. The physics is counterintuitive, and it begins with light itself. In these stars, radiation pressure can dominate, meaning photons are doing much of the work of holding gravity back. When the photons change form, the support changes with them. In extremely hot cores, gamma-ray photons can convert into electron-positron pairs. That conversion steals pressure support because radiation pressure drops when photons become rest mass. The core softens, contracts, and heats further. A feedback loop forms, driven by the star's own radiation field. The star is undone by the very light that once held it up. The instability does not begin at the surface, where we watch the star shimmer. It begins deep inside, where temperatures reach billions of degrees, and photons carry enormous energies. Pair production changes the effective adiabatic index of the gas, making it easier for the core to compress. Compression raises temperature, which makes more energetic photons, which makes more pairs. The loop accelerates until nuclear burning responds explosively. The outcome depends on how far the instability runs. In pulsational pair instability, the contraction triggers explosive oxygen burning that ejects mass, but the star survives. It can pulse multiple times, shedding shells in violent episodes. The pulses can be separated by years, decades, or longer, depending on the core's recovery and subsequent evolution. The final collapse may come later, after the core regains stability and continues evolving. Those pulses matter because they create dense shells at specific radii. When the eventual supernova or collapse shock arrives, it can crash into those shells. The collision can produce superluminous transients that look like the universe is cheating. In reality, it is stored energy being cashed out. The brightness is not magic, it is bookkeeping. The shells themselves can be visually striking in our reconstructions. Imagine concentric, semi-transparent bubbles expanding into space, each carrying dust and heavy elements. Some shells may be asymmetric, shaped by rotation or a companion's gravity. Others may fragment into clumps, leaving gaps where later ejecta can stream through. When the shock catches up, the collision front can light up like a ring, then break into hotspots. In full pair instability supernovae, the instability is strong enough to unbind the entire star. The explosion can be so energetic that no compact remnant remains. The star is dismantled into expanding debris, leaving no neutron star and no black hole. It is an ending that erases the engine. The core does not collapse into a point. It detonates into a cloud. This idea has a history that mirrors the development of nuclear astrophysics. In the mid-20th century, as scientists began to map nuclear reaction networks, they realized that extremely massive radiation-dominated stars could behave differently. Pair production, once a particle physics curiosity, became an astrophysical lever. Later, models connected these explosions to distinctive nucleosynthetic yields. The concept matured as computing power allowed more realistic stellar evolution calculations. Theory ties these outcomes to helium core mass and to the star's initial mass, with strong dependence on mass loss. Roughly, pulsational pair instability is expected for helium cores of several tens of solar masses, and full pair instability for larger helium cores. The exact boundaries shift with rotation, mixing, and metallicity-driven winds. The uncertainty is part of the story, because nature does not label its cores for us. We infer the core from the light, and the light can lie. Rotation matters because it can mix fresh fuel inward and move ash outward, changing how quickly the core grows. It can also support the star slightly against gravity, altering central conditions. Mixing can blur the neat onion picture, making shells less distinct and composition gradients less sharp. Even small changes in internal mixing can shift the star into a different fate category. The ending is sensitive to the path, not just the starting mass. Metallicity returns as a controlling parameter, not a background detail. Stronger winds at higher metallicity can peel mass away, shrinking the helium core and avoiding pair instability. Lower metallicity can allow the star to retain more mass, pushing it into the pair instability regime. The early universe, metal poor by definition, becomes the natural theatre. In that theatre, the monsters may have been more common, and their deaths more extreme. That is why pair instability matters for cosmology. A full pair instability supernova can produce large yields of oxygen, silicon, and other alpha elements, imprinting a distinctive chemical signature. It can also produce relatively little of some iron peak elements compared with other supernova types, depending on the model. It can enrich pristine gas quickly, changing the cooling and fragmentation of later star-forming clouds. It is a mechanism for turning a simple universe into a chemically complex one. Chemical enrichment is not just a list of elements, it is a change in physics. Metals provide additional lines for radiative cooling, letting gas shed heat and collapse into smaller fragments. Dust grains, built from those metals, offer surfaces for molecules to form and can shield interiors from harsh radiation. Once the first explosions seed the medium, the next generation of stars can form with different masses and different lifetimes. A single extreme death can alter the statistical future of a region. Pulsational pair instability matters differently. It can eject shells rich in processed material without destroying the core. It can create unusual transients and unusual circumstellar environments. It can also change the final remnant mass by stripping the envelope in bursts. In some scenarios, the star ends as a core collapse supernova after it has already thrown off much of itself. The final collapse then happens inside a self-made maze of debris. Now we pivot to the eeriest pathway, direct collapse. The same gravitational collapse that can power a supernova may instead fail to launch a visible explosion. The shock may stall and never recover, or it may revive weakly and then fall back. The star can collapse into a black hole with minimal light. In a universe built on luminous signals, this is an ending that tries to hide. This is the idea of a star that vanishes. A luminous supergiant can simply stop shining, leaving behind an absence where a beacon used to be. The transient could be faint, perhaps a weak outburst as the envelope responds, or a brief infrared signal as dust forms. The most reliable messengers might be neutrinos and gravitational waves, not photons. We would learn of the death by what is missing, not by what appears. The physics of a failed explosion is subtle, because failure can still involve violence. As the core collapses, neutrinos carry away energy and mass, slightly reducing the gravitational pull on the envelope. That sudden change can unbind a small amount of material, producing a weak shock in the outer layers. The star might brighten briefly, then fade as the remaining envelope falls inward or drifts away. Even a quiet ending can have a whisper of motion. Direct collapse is not just a theoretical curiosity, it is a way to reconcile energies and masses. If the envelope is tightly bound, or if the core is massive enough, the explosion energy may be insufficient. Material falls back onto the proto-neutron star, pushing it over the limit into a black hole. The final state is heavy, and the light can be small. The star's mass becomes a trap, not a trophy. This pathway also connects to the documentary's theme of limits. The brightest stars live near the Eddington balance and shed mass to survive. If they still retain enough core mass, the end can be a black hole that forms quickly. The monster's light fights gravity for millions of years, then gravity wins in seconds. boundary between star and remnant can be crossed almost instantaneously. We keep the competing endings alive because observations are still sorting them. Some supernovae are missing expected progenitors, hinting at failed explosions. Some transients are too bright, hinting at dense circumstellar interaction. Some chemical abundances in ancient stars hint at rare, extreme nucleosynthesis pathways. The universe leaves clues, not a single script. Each clue is partial and each comes with uncertainties. The search for failed supernovae has even become a kind of astronomical stakeout. Surveys repeatedly image nearby galaxies, looking for luminous supergiants that simply disappear. The method is simple in concept and difficult in practice, because dust, variability and crowding can mimic a disappearance. Yet the idea is powerful. If a star's light goes out and does not return, gravity may have taken it. What does it mean to see an event that produces almost no photons? Regardless of pathway, these deaths are the universe's heavy element foundries. Core collapse supernovae synthesize and eject oxygen, neon, magnesium, silicon, sulfur, calcium, and iron group elements. Explosive nucleosynthesis and neutron capture processes create rarer species under specific conditions. The rapid neutron capture process may occur in some supernova environments, though its dominant site is still debated. The periodic table is not a static list. It is a record of stellar catastrophes. Even when a black hole forms, not all material necessarily disappears. Some outer layers can be expelled before the final plunge, and some material can form an accretion disk that powers outflows. In certain cases, jets can punch through the star, producing high-energy transients. The details depend on rotation, magnetic fields, and how the collapse proceeds. The line between silent and loud can be thin. We connect this to the opening hook by reframing what swallowing means. A monster star can engulf or sterilize a planetary system in life. In death, it can seed countless future systems with the atoms that make rocks, oceans, and biology possible. The solar system disappears inside the thought experiment, then reappears as chemistry. The same event that ends one star can begin many worlds. Feedback is the bridge between single-star endings and galaxy evolution. Supernovae inject energy and momentum into the interstellar medium. They drive turbulence, heat gas, and can launch outflows from star-forming regions. They can trigger new star formation by compressing clouds, and they can suppress it by dispersing gas. The balance depends on density, geometry, and timing, on whether the blast hits a cloud or escapes into a cavity. Winds from massive stars already pre-shape this feedback, carving bubbles and sweeping shells before the explosion. The supernova then expands into a medium that is not uniform but structured by earlier mass loss. The efficiency of energy coupling depends on that structure. A shock expanding into a low-density bubble can race outward, while one hitting dense clumps can radiate and stall. The galaxy's ecology depends on the details of stellar weather. In visual terms, the interstellar medium is not a smooth fog. It is a tangled web of filaments, cavities, and knots, lit by starlight and stitched by magnetic fields. A supernova remnant expands like a growing lacework, bright at its edges where shocks heat gas. Over time, the remnant cools, fragments, and merges back into the background. The debris becomes part of the next generation's raw material. On larger scales, repeated explosions help regulate star formation in galaxies. They contribute to the multi-phase interstellar medium, with cold molecular clouds embedded in warm and hot gas. They enrich the circumgalactic medium, where metals can later rain back down. Galaxies evolve through this cycling, not through isolated events. The story is less like a single blast and more like a long conversation between stars and gas. Metallicity again changes the feedback loop. More metals increase cooling efficiency, allowing gas to radiate energy and collapse more readily. More metals also increase dust content, which changes opacity and chemistry in star-forming regions. Dust can shield molecules from ultraviolet radiation, helping clouds survive and fragment. The first generations of massive stars therefore change the rules for the generations that follow. They are not only actors, they are rule makers. Now we tighten the focus on remnants, because endings leave compact objects. A successful core collapse can leave a neutron star if the core mass stays below the maximum stable limit. That limit depends on the equation of state of ultra-dense matter, which is still uncertain. A heavier core, or strong fallback, can produce a black hole. Pair instability can leave nothing at all, which is a different kind of remnant, an absence that still shapes populations. Neutron stars are themselves extreme boundary objects. They pack more than a sun's mass into a sphere about the size of a city, supported by neutron degeneracy pressure and nuclear forces. Their magnetic fields can be trillions of times stronger than Earth's, and their rotation can be rapid enough to sweep beams through space like lighthouses. When we see a pulsar in a supernova remnant, we are seeing the core's survival made visible. When we see no remnant, we have to ask why. Black hole masses are not only set by initial mass, they are set by mass loss history. Strong winds at higher metallicity peel mass away, producing lighter remnants. Lower metallicity allows heavier remnants, because the star retains more of its mass until collapse. Across cosmic time, as metallicity rises, the typical remnant mass distribution shifts. The universe's chemical evolution becomes a quiet sculpture of black hole populations. This is where gravitational waves enter as a new observational channel. LIGO, Virgo and Kagra have detected mergers of binary black holes with masses that challenge older expectations. These binaries are fossils of massive star evolution, shaped by winds, supernova kicks and binary interactions. Their mergers are the aftershocks of stellar death. The signal lasts seconds in our detectors, but it encodes millions of years of prior history. Gravitational waves are ripples in space-time itself, predicted by general relativity, and first directly detected in 2015. Unlike light, they pass through gas and dust with little attenuation, carrying information from otherwise hidden regions. The waveform's chirp reveals the masses and spins of the merging objects, and the final ringdown hints at the newborn black hole's properties. In a sense, the universe is ringing like a bell, and we are learning to hear it. What other silent endings might become audible as detectors improve? Binary evolution adds another layer of competing pathways. Two massive stars can exchange mass, strip envelopes, and alter core growth. A star that would have ended as a red supergiant alone may be stripped into a compact helium star by its companion. The pair can survive supernovae as a bound system, or be disrupted by kicks. They can form black holes that later inspiral through gravitational radiation. The final waveform becomes a compressed autobiography. The geometry of mass transfer can be dramatic in visualization. Gas can stream through the inner Lagrange point, forming an accretion disk around the companion. The disk can launch winds of its own, removing angular momentum and changing the orbit. Common envelope phases can shrink separations rapidly, as the stars plow through shared gas and lose orbital energy. These processes decide whether the black holes end up close enough to merge within the age of the universe. Metallicity affects merger populations because it affects wind-driven mass loss, and therefore black hole masses. Lower metallicity can produce heavier black holes, which produce stronger gravitational wave signals at given distances. It can also affect binary separation evolution through mass loss and angular momentum changes. The cosmic merger rate becomes a function of chemical history. In this way, chemistry and gravity become partners in the same narrative. We connect this back to the documentary's earlier emphasis on environment. The LMC's lower metallicity was not just a measurement convenience, it was a hint about universal variation. In metal-poor galaxies, massive stars may retain more mass and collapse into heavier black holes. In metal-rich galaxies, winds may lighten remnants and change which explosions are visible. The same initial mass can lead to different outcomes in different cosmic neighborhoods. We also return to the unresolved mass ejection mechanisms from earlier chapters because they now matter for death. Rotation, convection, pulsations, opacity bumps, magnetic fields, and companions can all shape pre-supernova mass loss. That mass loss sets the circumstellar density profile that controls shock interaction. It also sets how much mass remains to collapse. The star's final spectrum is therefore partly a record of its final shedding. Evidence can discriminate among mechanisms by reading geometry and timing. Spiral patterns and equatorial tori suggest binary shaping and angular momentum. Random clumps and arcs suggest convection-driven ejections and stochastic instabilities. Periodic shells suggest pulsation-linked episodes, possibly amplified near local Eddington conditions. Each pattern is a signature, like handwriting in gas. We can also ask what these patterns imply about predictability. If mass ejection is stochastic, then two similar stars may end very differently. If it is tied to specific instabilities, then certain precursors might be expected before collapse. Observers search archival images for pre-supernova outbursts, trying to catch a monster in its last warnings. The universe may be giving us hints, but we're still learning the language. The key point is that largest was never only a number, and now ending is not only one event. A star can die in one explosion, in repeated pulses, or in near silence. It can leave a neutron star, a black hole, or nothing. The monster's boundary problem becomes the universe's inventory problem. What survives, what escapes, and what is locked away. We widen the lens to cosmology, because these endings scale up. The first massive stars, likely formed in metal-poor gas, lived briefly and died violently or silently. Their ultraviolet light helped reionize the universe, changing the transparency of space. Reionization is a phase change on cosmic scales, turning neutral hydrogen into an ionized plasma that transmits light differently. These early monsters may have helped lift the fog. Their metals enabled efficient cooling, enabling smaller stars and long-lived planetary systems. Without metals, gas cools poorly and tends to form more massive stars, which burn out quickly. With metals and dust, cooling pathways multiply, and fragmentation produces a broader range of stellar masses. The universe becomes more diverse as it becomes more chemically rich. Complexity, in this sense, is an emergent property of stellar death. Their black holes may have been seeds. Some could have grown by accretion and mergers into the massive black holes found in galactic centers. Others could have remained as stellar mass black holes, later merging and lighting up detectors with space-time ripples. Either way, monster stars connect early chemistry to later structure. They are bridges between the first light and the modern cosmos. We keep the mystery because the data is still incomplete. Pair instability supernovae are rare and hard to confirm unambiguously. Their light curves can resemble other power sources, and their spectra can be shaped by circumstellar interaction. Failed supernovae are hard to prove because absence is not a spectrum. Direct collapse may announce itself only through neutrinos, faint transients, or the sudden disappearance of a known star. Yet the direction is clear. The most extreme stars are not curiosities, they're engines that helped build complexity. They set chemical baselines, regulate star formation, and populate the universe with compact remnants. They turn short lifetimes into long consequences. When we map galaxies, we are partly mapping the integrated results of these brief violent lives. Transition. The camera pulls back from the dying star to the galaxy that absorbs its debris. The final chapter returns to the opening question with a cosmological perspective on limits. From this distance, a supernova remnant is a faint ring, and a direct collapse is barely a footnote. Yet the cumulative effect is unmistakable, because galaxies remember what happens inside them. Metals spread through spiral arms and halos, and hot gas vents into the circumgalactic medium. Over billions of years, the galaxy becomes a layered archive of stellar endings. The monsters are gone, but their fingerprints remain. We end with the thought experiment reframed one last time. A star so luminous it feels like 10 billion suns is not only a threat to nearby worlds, it is also a factory for the atoms and remnants that make worlds possible. The monster swallows the solar system in imagination, then gives the universe the tools to rebuild it. And the final question hangs in the quiet after the blast. How many of the universe's most important endings happened without anyone seeing the light? We return to the thought experiment that started the trap because it is simple enough to be dangerous. Put the monster where the sun is, then ask what disappears, and just as importantly what survives in altered form. Overlay the solar system again, but keep the labels honest and the scale unforgiving. Mercury at 0.39 AU is the first test, a tight loop of rock and metal. Venus at 0.72 AU is the second, bright but airless in this imagination. Earth at 1 AU is the line we feel in our bodies, because it is the orbit that defines our normal. On screen, the orbits look like delicate wire rings floating in darkness. The sun becomes a pinprick at the centre, and then the pinprick is replaced by a swollen, dim red disk. The disk is not a clean circle either. It has a soft edge, like fog lit from within. For red hypergiants, the radius estimates can reach past Earth's orbit in the most extreme cases. Some published radii reach toward Mars at 152 AU, depending on the method and the wavelength. A few claims brush the asteroid belt in their most generous definitions, where edge means a shell rather than a surface. The point is not the biggest number, because the biggest number is often the least stable. The point is which boundary that number describes, and what physics makes that boundary real. A star's edge is not a wall, and it is not even a single layer. It is a depth where the gas becomes transparent enough to let photons escape without being immediately scattered again. In practice, we pick an optical depth and call it a photosphere, because we need a reference surface to measure. That choice is practical, but it is also a confession. The star is a gradient. Opacity is the hidden lever, because opacity decides how far light can travel before it is absorbed or redirected. Change wavelength, change which atoms and molecules dominate the absorption, and the apparent radius shifts. Even the same star can look compact in one band and bloated in another, like a coastline that changes with the tide. In visible light, molecules like TiO can thicken the atmosphere and push the apparent surface outward. Those molecules form only when the gas is cool enough, so they mark an outer realm of the star's extended envelope. In the infrared, dust can dominate and create a larger pseudo-photosphere, where grains absorb starlight and re-radiate it at longer wavelengths. In radio and submillimeter, we can trace cooler gas farther out, but that is not the star's hydrostatic body. It is material already on its way to becoming nebula, so when we say a star could swallow the solar system, we must finish the sentence. Swallow which orbits, and by which definition of edge, and for how long. A planet can be inside a dusty shell while still outside the denser photosphere. A planet can be outside the photosphere and still be inside a wind that strips it, molecule by molecule. The visual implication is unsettling, because it is not a single engulfment moment. It is a layered invasion, where the first contact might be thin gas and dust. Then comes denser, hotter material, where drag and heating become lethal long before any surface arrives. This is the synthesis of the boundary problem, and it is why the trap works. Radius is measurable, but it is not singular, and it is not always the same kind of measurement. It is a family of radii tied to physics and to the bandpass, each one telling a different story about matter and light. The monster is real, but the outline is negotiated by the star, by the observer, and by the instruments. Now we reconcile the other trap because language invites a second confusion. Size, brightness, and mass are not interchangeable trophies, even when they travel together in headlines. A red hypergiant can win on radius because it is cool and inflated, like a low-density ember. A hot, ultra-massive star can be smaller in radius and still dominate in power, because its surface is a furnace. Luminosity is the documentary's provocation, and it is meant to pull us toward the ceiling. 10 billion suns is a lens on extremes, not a name tag for one confirmed star, and not a stable value for a single object. It is a way to feel the scale of energy output, and to ask what physics allows before a star tears itself apart. Real stars approach millions of solar luminosities, and brief transients can exceed that by far. The phrase points to the struggle near the limit, where nature's accounting becomes strict. Historically, this struggle is where stellar astrophysics became a science of constraints. Early astronomers could rank brightness in the sky, but distance turned that ranking into a puzzle. Once spectroscopy revealed temperatures and compositions, the Hertzsprung Russell diagram became a map of stellar lives. The most luminous stars gathered near the top, and the question became whether that top was a boundary or a coincidence. Stefan Boltzmann still anchors the comparison, because it ties glow to geometry and heat. Luminosity scales with radius squared and temperature to the fourth power, a relationship that punishes small temperature changes with huge luminosity swings. Cool stars buy area because they cannot buy flux, and their photons are gentler. Hot stars buy flux because their surfaces radiate brutally, and their ultraviolet output dominates their influence. On screen, the contrast can be made literal. The red hypergiant is shown as a vast, dim sphere with a trembling limb, its light smeared by dust. The ultramassive star is shown as a compact blue-white bead, surrounded by a halo of ionized gas that glows like a storm cloud. Mass sits in a different column, and it is the column that decides the ending. Mass sets gravity, core pressure, and fuel supply, and it sets how hard the star must push outward to avoid collapse. Luminosity rises steeply with mass in the high mass regime, but winds and instabilities rewrite the relationship as the star evolves. The most luminous stars spend their lives trying to stay bound, as if their own light is a constant escape attempt. A useful observation is that mass is not what we see directly. We infer it from motion in binaries, from spectral modelling, and from evolutionary tracks that assume certain physics. That inference is powerful, but it is also conditional, and the conditions matter most at the extremes. Transition. We stop ranking monsters by one number, and we ask what each extreme teaches. VFI Canis Majoris taught us that the largest looking stars are often the messiest, and the mess is part of the measurement. Its envelope is unstable and asymmetric, and its surrounding nebula looks like torn fabric frozen in space. The star's apparent size depends on scattered light, dust reprocessing, and a surface that is not a stable sphere. Even the idea of centre becomes slightly ambiguous when the outflow dominates the image. The lesson from VYCMA is physical, not just observational, because the star is operating near precarious balances. Near local Eddington balance and opacity bumps, the outer layers can become easy to lift. Opacity bumps occur when certain elements change ionization state, increasing how effectively radiation couples to the gas. Giant convection cells and pulsations can launch shocks that seed dust formation, and dust then becomes a sail for starlight. The star sheds mass in clumps and arcs, and those structures become part of what we measure. Visually, the nebula is a record of time, not just shape. Each knot and filament is a past episode, thrown outward and cooled, now glowing faintly as it drifts. When we measure the star through that debris, we are reading a layered history, not a clean boundary. WHG64 taught us how environment becomes a co-author, even when we think we are isolating a single object. In the Large Magellanic Cloud, distance is better constrained, so one major uncertainty shrinks. But metallicity is lower, and that changes how easily dust forms and how strong winds can become over long times. The star is wrapped in a dusty torus that shapes what escapes and what is reprocessed, turning geometry into a physical parameter. The lesson from WOHG64 is that we often measure a system, not a naked star, and the system has its own radiative logic. Radiative transfer models must decide where the stellar spectrum ends and the dust spectrum begins, and that decision affects temperature and radius. Inclination matters, because a torus can hide the hottest regions and emphasize cooler emission. Grain properties matter, because different sizes and compositions absorb and re-radiate differently. Clumping matters, because porous dust can leak light in some directions and trap it in others. Even with a good distance, the edge can still be ambiguous, because the edge is partly a product of what the dust allows us to see. The star becomes a lantern inside a sculpted shade, and we infer the lantern's size from the light that escapes. R136A1 taught us the opposite extreme, where the monster can be compact in radius and still be overwhelming in luminosity. Its atmosphere is a wind, and its spectrum is formed in outflow rather than in a quiet photosphere. The boundary is again an optical depth layer, but now it rides on ionized gas accelerated by light. The surface is not sitting still, and that changes how we interpret every line in the spectrum. The lesson from R136A1 is the upper mass frontier, where radiation pressure is not an afterthought. The Eddington concept becomes a practical constraint, modulated by opacity and composition, and it shapes which masses can remain stable. When luminosity approaches the Eddington limit, small changes in opacity can trigger large changes in stability. The star survives by paying with mass loss, and that payment shapes its fate, because the final core mass decides the death. These three examples also taught us how claims break, and why skepticism is part of the method. Distance errors square into luminosity errors, so a modest distance shift can produce a dramatic luminosity revision. Crowding blends sources and inflates inferred masses, especially in dense clusters where the brightest points are rarely solitary. Dust and extinction hide ultraviolet power and force us into model-dependent bolometric corrections, where the unseen light must be reconstructed. There is also a subtler failure mode, variability. Many extreme stars change on timescales from days to decades, and a single observation can catch them in an unrepresentative state. If the wind thickens, the apparent temperature can drop even when the core output remains high. If dust production spikes, the star can dim in visible light while brightening in the infrared. So what are the current limits, and what is still open, once we remove the mythology and keep the uncertainty? Empirically, single-star initial masses appear to top out around a few hundred solar masses, with large uncertainties that widen at the very top, The most extreme candidates sit in dense clusters where multiplicity is likely, and where dynamical interactions are common. The ceiling may be physical, or it may be observational, or both at once, because the hardest objects to form are also the hardest to measure. Theory suggests several breaks that can cooperate, and none of them needs to be perfect. Radiation pressure on dust can hinder accretion in early phases, because dust absorbs starlight efficiently and transfers momentum to the gas. Ionization heating and outflows can disrupt inflow, carving cavities that change how material reaches the star. Stellar winds and eruptions can remove mass as fast as it arrives, turning growth into a balance rather than a march. Binaries and mergers complicate every limit because they offer shortcuts and disguises. A star that seems to violate a formation cap may be a product of collision, assembled from two already massive stars. A star that seems too bright may be two stars in one-point spread function, blended into a single measured source. Even when we resolve companions, mass transfer can create objects that mimic younger or more massive single stars, because the surface composition and luminosity can be reset. The upper limit is therefore not one number, and it is not even one mechanism. It is a distribution shaped by environment, metallicity, and cluster dynamics, and it may differ between galaxies. The question becomes which pathway dominates in which conditions, and how often each pathway is available. Disk accretion with polar vents can build very massive stars in some models, because radiation escapes more easily along the poles. Competitive accretion can feed central objects in dense clusters, where gravity funnels gas inward. Mergers can assemble extremes when densities are high enough, and when time is short. Measurement uncertainty remains part of the frontier, and it is not a temporary embarrassment. In the Milky Way, extinction and distance structure are persistent obstacles, because dust lanes and spiral arms complicate geometry. In external galaxies, crowding and background emission complicate photometry and spectroscopy, because the light is layered. In both cases, dust geometry and wind clumping can bias temperatures, radii, and mass loss rates, and those biases propagate into mass estimates. Future observatories refine these numbers by attacking the weak links one by one. Better parallaxes and proper motions tighten distances for nearby extremes, turning uncertain luminosities into anchored ones. Interferometry and high-contrast imaging separate crowded sources and resolve extended atmospheres, so we can see a symmetry rather than assume symmetry. Infrared and submillimeter instruments map dust and molecular layers that hide the true photosphere, and they reveal where the energy is being reprocessed. Spectroscopy at higher resolution test wind clumping and velocity structure, because line profiles carry the imprint of outflow physics. Time domain monitoring catches orbital motion in binaries and reveals episodic ejections, turning snapshots into narratives. With each improvement, the monsters become less mythical and more constrained. Yet the edge remains elusive because the edge is a physical process, and processes do not draw clean circles. Transition. We pull back from today's monsters and ask what they imply about the first light. The cosmological coda begins with a universe without metals, a phrase that sounds poetic but is chemically precise. Population 3 stars formed from hydrogen and helium with almost no heavy elements, because none had been forged yet. Without metals and dust, gas cooled less efficiently and fragmented differently, so the typical clump could be larger. Many models predict a top-heavy initial mass function, with stars more massive on average than today, even if the exact distribution is still debated. Metal-free atmospheres also change opacity and winds, and that change rewrites the life story. With fewer metal lines, line-driven winds weaken, and stars can retain more mass over their short lives. That retention could push early stars toward higher masses and different death pathways, including more direct collapse. The same physics we test in the LMC becomes a hint about the primordial regime, because metallicity is a dial we can turn in nature. Those first stars would have been brief and violent, burning through fuel at extraordinary rates. Their ultraviolet output would have helped reionize the intergalactic medium, changing the transparency of the universe itself. Their deaths would have seeded the first heavy elements, enabling efficient cooling and smaller stars later. They would have turned a simple universe into a chemically complex one, where planets and biology become possible. Some early stars may have ended as pair instability explosions, leaving no remnant at all. In that regime, high-energy photons create electron-positron pairs, reducing pressure support and triggering runaway collapse and detonation. Some may have collapsed directly into black holes, leaving little light and few immediate signatures. Some may have produced seeds that later grew into massive black holes in galactic centres, providing a pathway toward the giants we observe at high redshift. The early universe may have hosted objects that make today's monsters look tame, but only for a moment. If so, their evidence would be indirect, written into elemental abundances and into the demographics of black holes. It raises a quiet question. How many of the universe's most extreme stars were never seen, even in principle? This is where the documentary's central question resolves into a boundary statement, because boundaries are the true theme. Stars become enormous and bright by exploiting different axes of physics, and each axis has a different failure mode. Cool stars inflate radius through low temperature and extended atmospheres, and their edges become fuzzy because molecules and dust can survive. Hot stars maximize luminosity through high temperature and high mass, while fighting radiation pressure that tries to unbind them. Swallowing the solar system is therefore two ideas wearing one phrase, and the phrase hides the difference. In radius terms, some red hypergiants could engulf the inner planets, depending on how we define the photosphere and which wavelength we honour. In influence terms, the most luminous stars sterilize and strip far beyond their physical edges, because radiation and winds travel outward with little regard for our definitions. Either way, the solar system disappears because the star's boundary is not where its consequences stop. The extremes reveal where physics strains, and they show us the cost of staying luminous. Hydrostatic balance becomes precarious when radiation pressure rivals gravity, and the star's outer layers become negotiable. Opacity becomes destiny because it sets how light couples to matter, and coupling determines whether material is held or expelled. Mass loss becomes the safety valve that keeps a star below catastrophic instability until it cannot, and then the ending arrives quickly. They also reveal how environment shapes the monster, even when the core physics is universal. Metallicity changes wind efficiency and long-term mass retention, shifting which stars can stay massive. Dust geometry changes what we infer and what the star can shed, because dust both hides and carries away energy. Cluster density changes whether mergers are plausible and whether a single star is ever truly single, even if it looks isolated. So the biggest stars are both measurable and elusive, and that tension is the honest conclusion. We can estimate radii, luminosities and masses with real data and real error bars, and we can improve those error bars. Yet the most extreme objects blur their own boundaries with winds, dust and crowding, and that blurring is part of their nature. The closer we get to the limit, the more the measurement becomes part of the phenomenon. This is the final meaning of the edge of the possible, and it is more than a ranking exercise. These stars do not just threaten planets in imagination, because their real role is constructive as well as destructive. They are cosmic architects, brief and violent, and essential to the universe's structure. They build heavy elements, drive feedback, and leave compact remnants that reshape galaxies. They show us a universe that tests its own rules, as if stability is an experiment repeated in different conditions. Stability is negotiated, not guaranteed, and the negotiation is written in winds and eruptions. Collapse is always waiting, and light can delay it only by paying in mass. The monsters live on the boundary between holding together and coming apart, and the boundary moves. We end where we began, with the thought experiment and its disappearing orbits, because it keeps us honest. The solar system overlay is a tool, not a claim of doom, and it is a reminder that scale is a kind of truth. It turns abstract numbers into a scale we can feel, then forces us to ask what the numbers really mean. It also forces a final question. When we draw an edge, are we describing the star or our own need for a line? The answer is that bigger is never one number, and it never stands alone. Radius, luminosity, mass, and environment weave together to create monsters that blur their own edges. By measuring them anyway, we learn where physics holds, where it strains, and how the brightest, briefest stars shape the cosmos. And the last mystery remains grounded in evidence, not in fantasy. If today's universe can still produce stars that push these limits, then the early universe may have produced stranger objects we have not yet named. Some may have died without light, leaving only gravity and chemistry behind. Some may have left only black holes, or a faint gravitational echo, or an absence in the record where an extreme should be. The biggest stars teach us humility in the face of measurement, and courage in the face of uncertainty. They are both the most quantifiable beacons we have, and the least well-defined spheres we can draw. At the edge of the possible, the universe does not give us a clean line. It gives us a frontier. We began with a simple, honest replacement. Put a real monster star where our sun sits and measure what happens in units we trust. By the end, that thought experiment had unravelled into a deeper lesson, because the biggest stars are not defined by one number, or even one boundary. Radius depends on wavelength and optical depth, luminosity depends on temperature and surface area, mass hides behind winds and crowding, and environment, dust, metallicity, companions, can make a star look larger, brighter, or stranger than it truly is. VFR Canis Majoris showed us a hypergiant that refuses to sit still, shedding itself in clumps and arcs that become part of its measurement and part of its future explosion. WOG64 pushed the same problem into another galaxy, where a known distance steadies our math, but lower metallicity and a dusty torus rewrite what surface even means. Then, LAN36A1 carried us to the opposite extreme, where the star is compact and blisteringly hot, and the edge is carved by an optically thick wind, while radiation pressure threatens to unmake what gravity assembled. Across every chapter, the pattern stayed consistent, even when the details changed, because these objects are always negotiating with limits. They approach the Eddington balance where light fights gravity. They pay for brightness with violent mass loss, and they end their lives in ways that still test our models. Core collapse that may or may not explode, pair instability that can pulse, or erase a star entirely, or direct collapse that leaves almost no light behind. And in those endings, the monsters don't just die, they seed, sculpt, and sometimes silence the next generation, turning stellar evolution into cosmology through rionization, enrichment, and the first black hole foundations. So the largest star was never a trophy, it was a diagnostic, a stress test for how we turn photons into physical truth. Distance errors square into luminosity, dust can reroute a star's power into infrared, line-forming regions can masquerade as a surface, and unresolved multiples can inflate a single name into a myth. What we really measured, again and again, was the seam where observation meets theory, where physics holds, where it strains, and where the universe forces us to be precise about what we mean by size, brightness, and even existence. Back at the beginning, we asked how anything can shine like 10 billion suns and still hold itself together long enough to matter. The answer is that a star can seem ready to swallow a planetary system in more than one way, by an inflated fog-like radius or by a lethal flood of energy, and in both cases the edge is not a wall, but a moving definition shaped by opacity, winds, and time. As for 10 billion suns, it remains the provocation it was meant to be, because the closer a star gets to that kind of power, the more the universe charges interest. Radiation pressure, opacity bumps, and feedback during formation impose practical ceilings, and if anything approaches them, it does so briefly, shedding mass, rewriting its own atmosphere, and leaving behind evidence that can be easier to misread than to confirm. In the end, these monsters do not swallow the solar system so much as they dissolve the idea of a boundary, until orbit becomes drag, daylight becomes heat death, and surface becomes a probability. The brightest stars teach a quiet, unsettling truth. At the far end of nature's scale, the universe doesn't draw lines, it draws gradients, and our job is to learn how to read them. And maybe that is the real revelation, because every time we refine a distance, resolve a crowded cluster, or map a dusty shell in new wavelengths, we are not just ranking stars. We are measuring the limits of matter under pressure, the origin of the elements in our blood, and the short, brilliant lives that helped make a dark universe transparent enough to see. If you want to follow where this story goes next, watch the sky across every wavelength, because the next monster may be revealed as much by what vanishes as by what shines.